All right, everyone, let's get started. So today we're gonna do some tensor analysis, and currently we're in the mid of our way towards studying curvature. Everyone, let's get started. What's going on? Let me just close the stream. Today, yeah, okay, yeah. So let me just recap what we have so far. So this is a Riemannian space. You can think of it as a higher dimensional surface. Our definition of the Riemannian space is not rigorous. Okay. So the Riemannian space is a high dimensional surface, basically, intuitively speaking, equipped with a metric tensor. Metric tensor is denoted as Gij. With the help of Gij, we can define line element. This is what allows us to calculate things like length, angle, etc. on the surface. The line element expression is ds squared. So Gij x dxi dxj. Oh, I forgot to mention dxi is a coordinate system for the Riemannian space, a local coordinate system in most situations. Got x1, x2, and so on. All right, so that's the line element. And we wish to define the geodesics. So geodesics is basically a piece of arc that maximizes or minimizes the arc length. So this is a recap. Okay, if you've seen this already, this is meant to recap some of the notations and notions we covered so far. So first of all, arc length. So the arc length of a curve. So the curve lives on the Riemannian space. So the curve has the expression xi of t, where t is a parameter, say, between alpha and beta. So let's just draw that. Okay, so this is the curve. So now if we fix the endpoint, say A and B, we wish to find the arc, or the curve, that minimizes the arc length. So the arc length, as I was saying, is S equals the integral from alpha to beta. Actually, alpha, beta were Greek letters which are often used as indices. Let me just change that, okay? So starting from t0 to t1, these are the bounds for the parameter t. Okay, so the integral, it's the integral of ds, basically. So that's the integral of the square root of Gij, dxi, dxj. And of course, in the expression for the line element, the summation notation is assumed. Actually, because we have an independent variable t, we should write dxi as xi dot times dt. So let's fix that. So this is you can think of it as the tangent vector. Xi dot is the tangent vector of the curve. And speaking of tangent vector, the tangent vector lives in the tangent space at a point. Okay, so let's say if we pick an arbitrary point, this Riemannian space is called M. Okay, M is usually the notation or the label for manifold. Let's say this is a tangent space. Okay, let me rotate this a little bit. So you can think of it as the tangent plane of a surface, basically. A tangent, the tangent space is a vector space, whereas the Riemannian manifold or Riemannian space is in general not. So if this point is P, then we denote this is the Tm at P, or actually TPM. That's the notation. So that's the tangent space. And the tangent vector here, the tangent vector of the curve always lives in the tangent space. Okay, like this. Okay, so I forgot to add dt at the end. So that's the arc length. To extremize the arc length, hi Ego, thank you very much for joining the stream. The geodesics, extremize the arc length. Okay, and by a variational calculus, or by the calculus of variation, which we will not repeat here. It's quite long, but using the calculus of variation, this is something we did several days back. So now we're just going to state the result. By variational calculus, we have the geodesic equation. Geodesic equation read the following. Okay, we used here earlier, the curve is parameterized by an arbitrary parameter t, and we can also use a unit speed parameterization. A unit speed parameterization makes sure that for all parameter values, the tangent vector has the length of 1. So you can imagine tracing out the curve with constant speed. This is always doable. Okay, so yeah, thank you very much, Ego. So this is xi of s is the unit speed parameterization. Then the unit speed parameterization satisfies the following differential equation, aka the geodesic equation. And the equation is as follows. Using the calculus of variation, we're able to get the differential equation, that is d squared xr, okay, over ds squared plus big gamma, actually not r but tau, okay, tau d squared x tau over ds squared plus big gamma tau alpha beta times the product of the first derivative, that is dx alpha over ds times dx beta over ds as well. Okay, so this equals 0. That's the geodesic equation, where the big gamma is the Christoffel symbol. And in the latest episode, we did a few examples of the geodesic equations. We are basically calculating this big gamma. Is called the Christoffel symbol. It's equal to the metric tensor g tau sigma. That's actually the contravariant the contravariant metric tensor. Here I only written the covariant metric tensor. Let me just fix that real quick. The contravariant metric tensor is defined as the inverse matrix, basically, of the covariant metric tensor. Okay, let me find the definition. Contravariant metric tensor is g alpha I gij equals delta alpha j. Okay, so here now we can use the contravariant metric tensor. Contravariant metric tensor g tau sigma over 2 times the derivative of the covariant metric tensor d of g. Actually, I think I'll just this is also a review for me, because it's been several days I haven't done any tensor calculus. So the mnemonic, so to say, or the method to memorize the formula is as follows. So you write dg over dx plus dg over dx minus dg over dx, and then fix the indices. So here, the two lower indices in big gamma are alpha beta. So you put the alpha beta at the end, at the last g with a minus sign. All right, and the summation index sigma, in the Einstein summation notation, sigma appears in the last term on the denominator. So dx sigma. Okay. For the first two g terms, it should have, both should have a sigma term. A sigma index downstairs, which is how the pattern is like. And you put the two lower indices in big gamma, one up and one down. So like this. So alpha top, beta bottom, and beta top, alpha bottom. So that's the way to memorize the formula. It's quite a complicated formula, okay? And the best way to internalize this is to do a bunch of calculations, okay, which we did a few weeks ago. I mean, not a few weeks, but a few days ago. So where are we heading now? So this is the Christoffel symbol. So far, it just appears to be this big complicated expression, coefficient, appears in the geodesic equation, right? Of course, that's one valid way to derive it, but it is still unclear what this does, right? What the geometric meaning of the Christoffel symbol is, because we know the geometric meaning of the metric tensor. So it allows us to do geometry, right? It defines the inner product, basically. So that's kind of nice. However, the Christoffel symbol is quite a complicated monster. This is a Christoffel symbol. And our goal today is to define and to understand the, how do you spell Christoffel? Double F, right? Double F, Christoffel symbol. And most specifically, Christoffel symbol of the second kind. We haven't seen the Christoffel symbol of the first kind yet. Okay, it's in one of the exercises in a book by Harry Lass. Yeah, the book name is in the description. Is the Christoffel symbol of the second kind. The book is called Vector and Tensor Analysis. It's a great book, although a bit short, a bit terse. Let's just put it that way. So a great exercise. Unfortunately, we only managed to do, not managed to, but only have time to do a few of them, just a handful of those exercises, and which I think it's a great shame, because you can only practice. I can only practice the fundamentals using the exercises. We'll see if this will become a bit of a problem for us later. Okay, so this is what we understand so far. Our goal is to define the so-called covariant derivative, as the title of the stream suggests. Right. So our goal is to understand covariant derivatives. This is quite a tricky notion. Define covariant derivative. And the textbook description for this one is rather short. So I'm not sure if I can completely understand this simply from the textbook by Harry Lass. That's why I listed two more additional resources in the stream description. One is the textbook by Professor Pavel Greenfield called Tensor Calculus and the Calculus, Tensor Analysis and the Calculus of Moving Surface. So this is our material, okay, material for tonight. Of course, we're going to use the original textbook we've been using for the Tensor Calculus series. It will be chapter 8, I was saying, a vector and tensor analysis. by Harry Lass. And the second resource I was mentioning, I was just saying that it's called Tensor Calculus, Tensor Analysis, and the Calculus of Moving Surface. Professor Pavel Greenfield is also a fellow YouTube creator. His channel's name is Math the Beautiful. If you go to his website, you will see it. It's in the link. It's in the description. Link in the description. That's his personal website, but it has the link for his YouTube. And the calculus of moving surfaces. Okay, I mean, just a vision of mine, I hope these live streams will form the foundation of my own series on tensors in a more unified fashion, because I find the field, tensor analysis, to be quite, so to say, separated in the sense that sometimes it's presented in this indices notation, which I'm doing right now. And on the mathematical side of the presentation, you see this coordinate-free notation full of this dreaded big O times symbol. And I think it causes a lot of confusion for beginners, like which one should you learn and how are they related, that kind of stuff. So it is my objective, it's a long-term goal, to sort of present both languages simultaneously. I think it's a good exercise for students of applied mathematics, because we really wish to understand both the pure mathematician as well as applied scientist. This one is by Pavel Greenfield. So that's another resource I'll be using, very likely will be using, to understand the covariant derivative. And lastly, it's the Tensor Calculus playlist by Chris. So Tensor Calculus playlist by Chris is very much from a physicist point of view. In particular, the central objective is to do general relativity with tensor calculus, perhaps the most widely known application of tensor calculus. Of course, it's a great series. And over there, the covariant derivative was defined at 4 different levels. So this is really a subtle topic. And playlist by the YouTube channel Chris. Because as I was saying, Chris approached the topic of covariant derivative from 4 different levels, which is quite amazing. And I hope I think at some point I'll be checking out his videos in general. I just wanted to re-chat. Okay, sorry, I was just talking. I wanted to re-chat. So I realized differential forms are patterns that come up with using multivariable calculus. Exactly, you're completely right. And defining those patterns in algebra. Yes, totally. So, for example, as Chad is saying, differential forms already encountered in multivariable calculus, in the sense that, for example, the change of variable formula, the multivariable change of variable formula, you can think of it as a U substitution in multivariable calculus. Right? The formula with the Jacobian, very famous one. That's arguably the first time someone encounters differential form, most likely to be. And so that those integrals and differential manipulation can be done without too much thinking about the algebra differential form. Yes, that's that's I would say a rather primitive goal is to do calculus, but it turns out that the differential calculus is much more powerful than that. But yeah, the differential form, for example, is used in topology to study topological invariances. It's once again, it's also a very not difficult, but rather advanced topic, usually taught at graduate level. Hi, Mr. Ming. Thank you for directing me to so many incredible other math creators. They're hard to find by using YouTube search bar. Yeah, that's a shame. That's a shame. So, Pavel Greenfield is a fellow YouTuber as well as Eigen Chris. If you're interested in tensor calculus, actually, don't treat my channel as the primary source. Okay, these are actual people who use tensor calculus in their research, in their teaching, and whatnot. I'm just a novice right now because I came from a heavily. So my primary background is stats. My primary background is stats and then applied mathematics, and more on the stats side of applied mathematics, like stochastic calculus, stochastic process, that sort of thing. The reason I recently decided to study tensor analysis seriously, well, I did do a self-study in undergraduate, but I just didn't have opportunity to use it because it's kind of different from my field of study and research in grad school. So my knowledge kind of atrophied. I didn't have time to do much exercises back then, so that was another major issue. So just kind of after 10 years, I barely remember anything other than, oh, I know the summation notation. So yeah, the bottom line is don't treat my current content as the primary source on tensor calculus. This is just a guy trying to figure things out, okay, trying to improve. But these guys, they really know what they're talking about, okay? So this is just my goal, okay? I might succeed, I might fail. So it's like, it's like if watching somebody streaming playing video games. Like, you can't guarantee he will win every match, right? But I'll try my best, okay? So that's our goal. And one fact I would like to mention, oh, by the way, how tensor is related to differential form. It's a great question. It's a great question, actually. So differential form is actually a special kind of tensors. Differential form is actually a special kind of tensors. So in a modern definition of a tensor, we think of tensors as multilinear forms. That is, it is a scalar valued function that takes vectors or covectors as input. So covectors are elements of the dual space. Okay, so I know. Sorry, let me restart. Okay, so actually, let me write something. This is on the side. So the modern definition, which we briefly covered in our earlier stream called tensor analysis, modern versus classical. We're doing mostly classical. Modern, how do you spell? Okay, modern tensors. Modern definition of tensor is a tensor is a multilinear form. It's got a multilinear form. So T, it takes elements from the vector space V. Let's suppose V is a real vector space. Okay, so you got copies of V, and then you have copies of V star. These are the dual space. The dual space are dual space is the set of linear functionals on V, which is itself a vector space. Okay, and it maps to, say, real. It's multilinear in the sense that for each argument of t is a linear function if you fix all the other arguments. So that's the definition of that's the definition of tensor in a modern sense, and which implies the classical definition. That is a bunch of indexed array that satisfies the transformation law. That's the definition we're using, and it's the most common definition you see in physics. But this is a modern definition, a modern algebraic differential geometric definition you find in mathematics, pure mathematics textbook. But what is a differential form? A differential form is a special kind of tensor. A differential form is a alternating tensor. That is to say, or exterior form. Differential form, exterior form are alternating tensors. So that is to say, if you exchange the order of two arguments, it picks up a minus sign. Or alternating tensor, that's it. So it's quite an elegant definition. Because exterior forms aims to capture area, signed area. Signed area not only gives you information about the area, but also orientation. Very much like determinant. Okay, so that's a very high-level definition, high-level description. But basically, a differential form is a subclass of tensors. Okay, so I do hope to continue this series in the form of more modern exposition. But the overall philosophy is to do this first we do the classical version, so that the modern definition don't feel like abstraction in a vacuum. Okay, so after we get some experience with working with concrete objects, then perhaps that will make the abstract definition more easy to digest, so you get a feel of how things are going. Although, logically speaking, you can just start from the modern definition and work from there. But it is my experience that somebody who is well-versed in the modern formulation can still have trouble reading the classic literature, which is really a shame. So with this reinforced my idea of bringing the two sides into a mutually intelligible exposition. So that's the goal, and I don't know how long it will take me to get there, but we hope to do so. And actually, going back to my original motivation of studying this stuff is to understand information geometry, which is currently another big area of application of differential geometry in probability, mathematical statistics, and machine learning. That is to use the tools of differential geometry to understand statistical inference tools or machine learning algorithm, that kind of thing. That's the overall objective. And actually, speaking of which, on Saturday we'll have our first stream on information geometry, just to give the basic idea how can statistical models can be treated as manifold, and how can differential geometry help us, and perhaps do some basic Riemannian geometry there. All right, so that's the big goal. And so coming back to our concrete goal tonight, that is to define covariant derivative, let's recall a crucial property of the Christoffel symbol. The Christoffel symbol, big gamma, is not a tensor. Despite the appearance of being a multi-indexed array, it is actually not a tensor. Why is that? Why is it not a tensor? Because it does not satisfy the transformation law for tensors. Okay, so this is what we really care about. So something needs to be, for something to be a tensor, it needs to satisfy the transformation law. And here's the transformation law for the Christoffel symbol. It reads like this. So gamma bar stands for the Christoffel symbol in the new coordinate system. So when we denote, this is our convention, okay, xi is the old coordinate. Okay, and through a coordinate transformation, we get x bar I. X bar I denotes the new coordinate system. You can think of xi as the Cartesian coordinate system of a plane and x bar as the polar coordinate. So big gamma bar, that's the Christoffel symbol in the new coordinate system. Big gamma bar ijk equals big gamma alpha beta gamma, and then times d. So let me just write it this way, okay? So as I said, this is not a tensor, but for the moment, if we pretend this to be a tensor, what should the transformation law be? For the moment, if we pretend this to be a tensor, what should the transformation law be? Well, let's use the rule we learned earlier. So it has three indices, so it should have three Jacobians, dx over dx, dx over dx, d over dx. Okay, there should be a bar somewhere in all of these Jacobians. I'm not writing that yet. Okay, we'll do that presently. So where should the bar be placed? Well, it's got one upper index. Suppose this is a tensor. Okay, suppose this is a tensor. It's got one upper index. So we mentioned earlier from our stream, way back, yeah, almost 2 weeks earlier, probably this one, actually even earlier than that, So this is a general definition of tensor, quite a monstrosity. But basically, what it says is, if it got an upper index, say a1 in the upper index, you should have a Jacobian of the form dx bar a1 over dx1 alpha, and alpha will be summed over. Okay, so what it is saying is, if you have a contravariant index, upper index, in the transformation law, you should have a Jacobian that looks like d new over d old. D new over d old. X bar, remember, is the new coordinate. So dx bar over dx, that's d new over d old. And how many copies of that do you need? Not really copy, but how many Jacobians do you need? For d new over d old, you need all of them to match the upper indices. Okay, and for the lower indices, there are s of them, b1, b2, all the way to bs. You need to pair them with the inverse Jacobian. That's the d. These are d old over d new. So that's the law for the transformation of tensors. Okay, so coming back here, we have one upper index, I. So for that, we need dxi on top. And also, because this is a contravariant tensor, it should be d new over d old, so you put a bar on top. So dx bar I, and then over dx alpha to contract the index. All right, and now the two Jacobians that comes after should be d old over d new. So bar goes down like this. Okay, and where should the index be? Where should the new index jk be? Well, it should be downstairs too, because the index jk is downstairs on the left. So j and k are downstairs, and beta gamma are summed over. So this is the transformation law, not for the Christoffel symbol, but for an actual tensor. The crucial idea is that it is not a tensor because it has an extra term trailing behind. And what will they be? They are d squared. This is something we derived earlier, so I'm not going to repeat that. So using the geodesic equation, basically, using the geodesic equation, you can derive the transformation law for the Christoffel symbol. Basically, we write the differential equation in two coordinate system and then compare. That's the overall idea, and from which we get the new transformation law. And the new transformation law looks like this. There's an extra term trailing behind, which makes it a non-tensor. Okay, so this is something extremely important. Not everything that looks like a multi-indexed array is a tensor. It needs to satisfy the tensor transformation law. And the Christoffel symbol, even though it looks like a third-order tensor, it is not one. Okay, so this is not a tensor. No, that's the transformation law. If it is a tensor, it should only have the first term, but there are two extra terms trailing behind, and the derivation was done in the previous episodes. Okay, so this is something that we will make heavy use of today. All right. Hi, Steve. Thank you very much for joining the stream. All right, so that's the Christoffel symbol, the second kind. And our goal is to define covariant derivative. So first, I will follow a Lass's exposition and try to understand that. Okay, but from just to as a fair warning, from my first attempt to understand Lass's exposition, I felt like, okay, it seems like I can follow the algebra, although I never performed it. It feels like I can follow the algebra, but the geometric meaning feels unclear. Okay, as if this is me 10 years ago, I would be rather frustrated and dismiss the book as useless. But now I'm a little bit older and more mature, if I do say so myself. I'm not going to bash the book. Instead, I'll try to find things I can learn from it. And I won't just bash the book because it is incomplete. Okay, so I proceed with this one because this is the shortest. This exposition is the shortest. So covariant differentiation is introduced as follows. So I'm reading the textbook verbatim right now. Let us differentiate the absolute covariant vector given by the transformation. So this is what we're going to differentiate. So let A I be an absolute covariant vector. I'll rechat in a bit. That is to say, it has the transformation law, AI bar equals A alpha. It's covariant, so you have a downstairs index, therefore we should pair that with a Jacobian that looks like D old versus D new. So dx over dx bar, and then we place the index upper x got the alpha, and the lower x got the I. So that's the absolute covariant. For example, let's consider AI to be an absolute covariant vector, and let's differentiate with respect to the new coordinate, because on the left hand side you got the new coordinate, right? the new component of A. So let's differentiate that by x bar j. Okay, so what are we doing here? So the idea is we have a vector field on the Riemannian space. So let's just draw a picture. So this is a Riemannian space, for example. This is a illustration of a curved surface. All right, and we have a coordinate system imposed on it. Coordinates, actually two coordinate systems, xi and xi and xi bar. So this is what the new coordinate system look like. Say this is the new coordinate system. Okay. Hopefully this chart will not look too cluttered. So these are the constant coordinate lines, constant xi bar. Right? You can always think of coordinate system as a bunch of coordinate lines, like a grid. Right? What is alpha? what is big A? Big A is, well, big A is, is a covariant vector. We know that covariant vector, they should live in a dual space. So they're supposed to be, they should be, you know what? Okay, I'm just going to visualize them as arrows. These are arrows living in a tangent space at each point. So you have a vector field on the curved surface, like this. The vector changes from point to point. Think of this as the Earth's surface, and at each point, at each city, there's currently a wind blowing from a certain direction with a magnitude, right? So that's the idea of a vector field on a manifold. They live in the tangent spaces at each point. Okay, so this is A. This is A. They have components. They have components relative to the coordinate lines. Okay, so with a coordinate line, you get the basis vectors, and then you can decompose the vectors onto them, and that's the component big A bar. And now we wish to differentiate with respect to the new component. Differentiate with respect to the coordinate. Right? The idea is, say, if a point goes from here to here, how does the component of the vector AI bar changes? Right? If you perturb the coordinate xj, what's the rate of change? So d over dxj on both sides, this will give us the following. So d a bar I over d x bar j on both sides, right, by the product rule on the right, you get, okay, dA alpha over dx bar j times dx alpha over dx bar I plus a alpha times, well, the second derivative. So you get d squared x alpha over dx bar j times dx bar I. Right? And we can, the first factor in the first term, dA alpha over dx bar j, can be rewritten as, because this is old component, right? So we like old versus old, new versus new, right? So on the left you got new versus new. So we wanted to write it in the form of old versus old. So you got dA alpha. Let's introduce the old coordinates, say dx beta times dx beta over dx bar j. So this is just the chain rule for the first factor. Just applying the chain rule for the first factor, all right? And then times dx alpha over dx bar I. dx bar I. And then plus the second term, which is unchanged. So take a look at this object here. Take a look at this object. That is the partial derivative of A. That is the partial derivative. So we're interested in the partial derivative of A. The partial derivative of the component of A. It is not a tensor either. Even though it's got two indices, it's not a tensor. The bottom line is the partial derivative of the component of a vector is not a tensor because of the extra term going on behind. So therefore, the textbook says it is at once apparent that dAi over dxj, the partial derivative, is not the component of a tensor. So the conclusion is observation. Because of this extra second order derivative term, very much like what's going on with the Christoffel symbol. You got this second order derivative term trailing behind. So observation is dAI over dxj is not a tensor. If it is a tensor, then you should only have the first term. So that's a bit of a bummer, because the crucial idea is that tensors corresponds to invariance. As we introduced that idea in our earlier stream called Tensor Analysis, Modern versus Classical. So this does not correspond to invariance. The partial derivative is an object that depends on the choice of a coordinate system, which we do not like. And then the text will go on saying, however, we can construct the tensor by the following device. Okay, so time for some trickery. Okay, so constructing a tensor. So this is what the author, Lass, is telling us to do. Construct the tensor by the following device. Okay, so we're going to use an identity. From the Christoffel symbol, which we already written down. That's basically this one. So let me rewrite it. Just want to double check this is the correct formula. Okay, in a bit. Yeah. Okay. Looks okay. So we're going to use the Christoffel symbol transformation law. By the transformation law, of the Christoffel symbol, so it reads like gamma bar, the new big gamma alpha, not alpha, but yeah, alpha ij. Yeah, that's the new big gamma, equals the old big gamma, gamma rho sigma tau. Rho sigma tau, let me just write the transformation law, d over dx, dx over dx, dx over dx, put the bars and indices later. Okay. 1 bar upstairs, 2 bar downstairs. Alpha should be on top. Rho down here. Ij down here. And sigma tau upstairs. Okay. So yeah, we have that. And also the second order derivative term. The annoying term which makes it non-tensor. D square x sigma over dx bar I dx bar j. Okay, and then times what? Times, oh, right, dx bar alpha over dx sigma. So this is the same formula for the transformation of the Christoffel symbols here. This one, same one. All right, and now we're going to multiply this by a bar alpha. Okay, so this equation is labeled as 519. Okay, this one is 519, and this equation is labeled as 520. And here's what it says. It says multiply 520 by a bar. Let's do that. Multiply 520 by a bar, because I really wanted to put these verbal instructions on the side, because, you know, guess what? The formulas are difficult to read. If you just do the algebra without mentioning what you're doing on the side, you might get lost later when you try to read your own notes, and often there's all typos involved, so it's a mess. All right, so this way we multiply a bar alpha on both sides. But once we've done that, there's a summation going on, because alpha is now a dummy index. Okay, so just bear that in mind. A bar alpha. Guys, I haven't been looking at chat yet because I just wanted to finish this derivation. I'll read chat soon. Okay, so multiplying a bar alpha on both sides. Okay, so this is a bar alpha, old gamma rho sigma tau, dx 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 dx. 1 bar upstairs, 2 bar downstairs, alpha upstairs, rho downstairs, sigma upstairs, I downstairs, tau upstairs, j downstairs. Okay, and then plus a bar alpha. Actually, you know what? I'll write a bar alpha here. A bar alpha times dx bar alpha over dx alpha. Hang on, that's not right. It should be sigma. Yeah, sigma. So I was saying, in tensor calculus, it's very easy to make typos in your notes because there's so many damn indices. D square x sigma over dx bar I dx bar j. Okay. So what can we do here? Can this be transformed? Can this be transformed? So because we have the transformation law earlier, what is this equivalent to? So can we, if we multiply Jacobian on both sides, that would mean ai bar dxi dx bar I over, say, dx beta. If we multiply this Jacobian on both sides, we will get a alpha dx alpha dx I bar dx I bar over dx alpha, and this is just a Kronecker delta. This is a Kronecker delta alpha beta, and this is a beta downstairs, a beta downstairs. So the point is, you can write the old components in terms of the new ones too. A beta, let me just put it down next to the formula we're currently manipulating. So a beta is a bar I dx bar I over dx beta. Okay, so you have this formula. Put it on the side and compare. See, can we use this? Yes, we can. This one is what? This one is just a sigma. This is just a sigma. Take a look. Alpha is contracted. This is just a sigma. Okay, and can we do something similar on the right? You got a bar alpha here. Yeah, these two can be combined. Let me just change the order of those two so the notes looks cleaner. So these two factors combine. They're just old A, old component A with index rho down here. Okay, so this is what multiplying 520 on both sides by A alpha does. Okay, so we have that, and and it says subtract this equation, subtracting from 519. Right? This is 519. This is 519. So what is going on here? Okay, so this is 519. We want to subtract the two equations. All right, so it's difficult to, because they're not on the same. Can I maybe just zoom in a little bit? Is that better? Yeah. So the difference between the left-hand side is what? 519 minus this result we have earlier. So that's dA bar I over dx bar j minus a bar alpha gamma alpha ij. So that's the left-hand side. Let's write that down. So 519 minus above gives us d here, over here, d a bar I over dx bar j minus a bar alpha downstairs, yeah, and then big gamma alpha ij. Okay, so yeah, that's the difference between the left-hand side. On the right-hand side, is there any common factors? Hopefully there are some common factors. What are the dummy indices? Because sometimes you can rename the dummy. I mean, you can always rename the dummy indices. On 519, the dummy indices on the right are I and j. Yeah. I and j. Are we? Yeah, I and j should be both lower indices because I is a lower index. That's right. And just like what's going on here, rho is not a free index, sigma is not, tau is not. They all get contracted. Ij are free. Here, Ij are free. So this is actually quite nice. The point is that the last term cancels. The last term cancels, and you just have this factor, which is the two Jacobians as a common factor. So that's cool. You get dA alpha over dx beta, this factor here, and then we got to change the index so that alpha and beta becomes a new dummy index down here. Change sigma to beta, tau to alpha, all right? And you get gamma. Should we use rho? Yeah, we can use rho, it doesn't matter. A rho, gamma rho, alpha beta times the inverse Jacobians. The two inverse Jacobians, you get dx alpha over dx bar I times dx beta over dx bar j. And guess what? This combination, this special combination is a tensor. This is unlike the ordinary partial derivative, which is not a tensor. This is a tensor. This is a covariant second order tensor. Let's write that is 0 upper index, 2 lower indices, so that's a 0-2 tensor. So that's why we can construct a tensor from a non-tensor. Okay, so that's kind of cool, and we're going to give this a notation. So define A. This is a notation used in LAS. Okay, if it differs from the notation you're used to, I'm just using the notation in the original book. So this way it helps me compare with the original source. So eventually, I hope to consolidate my understanding into a consistent notation. But here, this is what the author used. Okay, so they put a comma between I and j to indicate covariant differentiation. So they put a comma here between the two indices I and j to indicate covariant differentiation. We'll say that again. So on the left-hand side, this is A bar ij. So A bar ij is d A bar I over d x bar j. All right. And what else? Minus A bar alpha gamma bar ij. This is the left-hand side. And on the right, well, it's just A alpha beta downstairs, two indices downstairs, as dA alpha over dx beta minus A rho gamma rho alpha beta. Okay, so there's that. And so that we have the tensor property, the A bar ij. Oh, remember, there should be a comma between, my bad, comma to indicate differentiation. Okay, so it's a comma and differentiate. Here is the same. A alpha comma beta to indicate covariant differentiation. So that the formula above now reads A bar I comma j equals A alpha comma beta times the two Jacobian dx alpha over dx bar I times dx beta over dx bar j. So this is what we have. Okay, so let me box all three formulas above, because these two are definitions, and that's the law for this new object, and this is called the covariant derivative. This is the covariant derivative for a covariant vector. Okay. This is called the covariant derivative of AI with respect to xj. The comma will denote covariant differentiation. Definition: covariant derivative of A alpha with respect to x beta. The comma denotes covariant differentiation. Okay, so we managed to cook up a tensor, so that's what we managed to do. But it's still unclear why this is important. Okay, why don't we to cook up a tensor in some other way? It's not clear, but at least we know a crucial lesson here. The partial derivative on its own is not a tensor, and to make it a tensor, you need to put an adjustment term, so to say, a correction term that involves the Christoffel symbol. Okay, so that's the main lesson here, even though the geometric meaning of this is still a bit murky right now, and that's okay. We can figure that out later. This is not meant to be a simple notion to be immediately understood. Okay, so at least we have this algebra. Okay, of course, for the Cartesian coordinate, there is no difference between the covariant derivative and the ordinary partial derivative, because in the Cartesian coordinate, the metric tensor is a constant. Yeah, in the Cartesian coordinate, if you're talking about the Euclidean space and Cartesian coordinate, then g will be a constant. Okay. It is not true that if you have the Euclidean space, g is automatically constant. No, not necessarily. You can still have things like the polar coordinates, where g is not a constant. Okay. So I'm just saying that imagine we consider the Euclidean space with constant metric tensor everywhere. Then the Christoffel symbol by this formula must vanish. The Christoffel symbol vanish, and therefore the correction term vanish. And in that case, the covariant derivative and the ordinary partial derivatives are the same. Okay, so that's a special case. Okay, and here, so that's the introduction to the covariant derivative. Okay, so hopefully everyone is still on board. Let me read chat for a bit. Differential Geometry of Curves and Surfaces by Docamo. Yeah, it's a great book. It's a great book. So that one is called Differential Geometry of Curves and Surfaces. Right, so that one is called Differential Geometry. For my liking, it spends perhaps a little bit more time in R2 and R3. I mean, nothing wrong with that. And there's also, of course, a lot of beautiful results in there. But for my purpose, I just wanted to get to the general arbitrary dimensional setup as quickly as possible. So I'm very much following what a physicist's path to general relativity. Yeah, it's a great book on its own. Differential Geometry of Curves and Surfaces. Actually, I own a copy. I believe it's a Dover's copy. So yeah, in the future, we'll do perhaps sort of a mini lessons on differential geometry of curves and surfaces in R2 and R3, purely using vectors alone. Okay, so the barrier of entry would be very low in that case. You just need to do regular calculus in Rn. Yeah, so that's a great mention. Thank you very much, Steve. Next year, this month, we'll make sure that I know real analysis, tensor analysis, etc., like an expert. Yeah, good luck. Good luck. In a year, you can definitely study a lot. I think that's a reasonable goal. Good luck. Good luck, Eagle. So here we have this new notion, right? We have this new notion, and let's see if we can try to extract some kind of meaning from this, right? That will be ideal. Okay. All right. So the textbook by Lass then continues on and say, for a scalar of weight n. For a scalar of weight n, what do we have? Remember, scalar is a special kind of tensor. A scalar in our context, it just means a tensor with tensor of zero rank, or zero order. So that means it can't just be a number. I mean, a coordinate component is a number, but that's not a scalar in the context of tensor analysis, because it depends on the choice of coordinate. Okay, a scalar has to be something that is independent of the choice of coordinate. So for a scalar, we have the transformation law. For a scalar A, okay, there's a new, for a scalar A of weight n. What do we mean by that? Now, once again, going back to the definition, which is 24 is here. This is the tensor, definition of tensor. Definition of tensor with of weight n. Weight n. So this weight n refers to the factor on the right hand side, the determinant of the Jacobian, dx over dx bar, d old versus d new, and then raised to the nth power. So this is what weight n means. If n equals 0, we say that the tensor field is absolute. Otherwise, the tensor field is relative of weight n. This is what it means. So if you have a scalar, then there's no Jacobian going on the right. Right? That's because, well, there's no index in a scalar. So it would just be a and a bar with this extra Jacobian factor to the n. So for a scalar of weight n, we have the transformation law. A bar equals dx over dx bar to the n. Okay, to be honest, I never actually seen a concrete example of a weighted tensor. Okay, I never seen a concrete example of this. I just seen in the definition. So don't ask me what on earth does this mean. Perhaps it's my own fault for skipping exercises, but this is at least the definition. Okay, for a scalar of weight n, we have this definition. And now let's see how does it behave under covariant differentiation. Okay, so how do we define, say, a covariant derivative for a weighted tensor, right? Because earlier we only used absolute tensor. This absolute tensor. Here we have a weighted tensor. In this case, the simplest weighted tensor, just a scalar. So from here, we need to take the derivative d over dx bar j, and see what we can get from here. Okay, so on the left, that's d a bar over dx bar j. On the right, okay, so first we have dx over, let's keep the Jacobian term constant for now, and then dA over dx bar, and we know we can use the chain rule and write dA over dx alpha times dx alpha over dx bar j. Yeah, that's the first term in the product rule. And now in the second term, you got, because this is a n's power, use the power rule, n times dx over dx bar, determinant to the m minus 1, and then times the derivative of the determinant, d over dx bar. It's quite a complicated expression. And then over dx bar j, and then times a. So the second term uses the power rule and the chain rule. Okay, what a mess, right? What a mess. So is there anything we can do to simplify this? Actually, there is. From very, very early on, when we discuss the determinants and Jacobian and all those kind of things, perhaps in the very first session, we managed to have an expression that can express this, the partial derivative of a Jacobian. So where is that? I'm just going to first write down the formula, and we'll go back to the notes we had earlier. So this term right here actually equals dx over dx bar, absolute value, not absolute value, but determinant, dx over dx bar determinant, times dx bar alpha over dx beta times the second derivative, dx d square x beta over dx bar j times dx alpha bar. Whoa, what a mess, right? What a mess. Where did we get this from? I believe it was from the very first session. This the 23rd. Yeah, 23rd. Here, going down. We talk about the determinant. In the 23rd, it's our first session. We talk about the summation convention, the determinant, and apply it to Jacobian. The cofactor stuff. Is it this one? Yeah, this one right here. This one right here. It says for y as a function of x, y stands for the n tuple y1 all the way to yn, and x stands for the n tuple x1 all the way to xn. So this one, d of dy over dx determinant, differentiate with respect to x mu, you get dy over dx times dx alpha over dy beta, and this is just the second derivative. This should be d squared y beta over dx mu dx alpha. So we're using this formula here. Okay. Yeah, very hard to predict, right? Things, when do things come in handy? Okay. So anyway, we derived this earlier. So now we're just using it here, and let's see what happens. This is this. Okay, so far we have on the left, this is unchanged. The first term is unchanged, and the second term just got, use the substitution, the green substitution here. You got dx over dx bar. Well, dx over dx bar gets combined with the determinant of dx over dx bar to the n minus 1, so just minus 1 disappears. There's that. And then dx, oops, blue color, dx bar alpha over dx beta times d square x beta over dx bar j dx bar alpha times a. All right. What the heck is this? It then says multiplying. Okay, this, by the way, this equation is 523. Okay, this equation is 523, and now it says multiplying. Consider the following. Consider the following equation. Okay, so we have. So this is what it claims in the text. So consider this identity: gamma bar alpha j alpha, gamma bar j alpha equals gamma sigma alpha sigma dx alpha over dx bar j. Okay, and then plus d squared x sigma. Once again, this just feels like unmotivated motivation. I know what you're thinking, because I'm thinking the same damn thing. I usually hate this kind of exposition, but I still do. But let's just try to follow it. Okay, and we'll look at some other sources soon. I just want to grind through this and see if there's a punchline somewhere. Okay, so it is claimed we have this property, this identity. Let's think about why. What is happening here? So it seems like we're using the transformation law for the Christoffel symbol and doing a contraction. And see how, let's see. Here, this is the transformation law right here, transfer 520. This is the transformation law for the Christoffel symbol. Here, we change the color. Okay, so how do we get this to what's claimed up there? We can, oh, by the way, I forgot to mention, Christoffel symbol has the property that the two lower indices are symmetric. So if you change the indices downstairs, it wouldn't change the Christoffel symbol. Just check that real quick, okay? This is the definition of the Christoffel symbol. Imagine exchanging the order of alpha beta. Okay, imagine changing the order of alpha beta. The factor up front, it's not affected. Changing the order of alpha beta keeps the sum of the first two terms the same. And because G is symmetric, G is a metric tensor, is always symmetric. So G alpha beta and G beta alpha are the same. So this way, this tells us that the Christoffel symbol is symmetric in the two lower indices. And here, we're just to get the claimed equation from the transformation of the Christoffel symbol, we just need to set I to be alpha. Okay, we just need to set I to be alpha, and let's do that. Setting I equals alpha. We get gamma bar alpha alpha j equals gamma rho sigma tau dx bar alpha over dx rho times dx sigma over d, because I is swapped to alpha, so you get dx bar alpha. And now what? And dx tau over dx bar j, and then plus d square x sigma over dx bar alpha dx bar j dx bar alpha and then over dx sigma. Okay, notice these two terms combines together and you get dx sigma over dx rho, and that's just the Kronecker delta. Kronecker delta sigma rho. So now you can swap index. You can change sigma to rho or rho to sigma, doesn't matter. So let's do sigma, change rho to sigma. So that's gamma sigma sigma tau. Okay, and dx tau over dx bar j. Dx bar j, and then plus the second term that trails behind. So it looks like we have what the claimed equation. Okay, so the claimed equation is now arrived. Consider claim, okay, and this is as claimed. So we have no problem with this equation now. So multiply this. It says consider this claim and multiply this by n a bar. Multiply the claim by n a bar. So what do we have there? We have, well, n a bar, big gamma bar alpha j alpha equals, well, n a bar big gamma sigma alpha sigma times dx alpha over dx bar j, and then plus n a bar. Still, I mean, it's still very unclear where this is going. There's very little intuitive explanation in the text. I find it to be rather frustrating. But once again, this is a very kind of a very short book, and in the same series as Baby Rudin, so it's kind of expected. But we'll try to dig some meaning out of this ourselves. Okay, so right now still we're just trying to follow the algebra. Okay, I try to swallow the frustration. Okay, temporarily. So hopefully this will become meaningful at some point. Okay, so this is what we're doing. We just multiply the claim on both sides by n a bar. Is there anything we can do? Is there anything we can do to simplify the right-hand side in some way? Remember, we have the transformation law here. We have the transformation law. Let's not forget that. So is there something we can do? Well, you got a bar here, and the Jacobian is not really helping because this is a scalar. You don't even need the Jacobian to do the transformation. So what is this about? Huh? What on earth is this supposed to be? Here we have, it says multiply the claim by n a bar. We get this, of course. It says subtracting from 523. Okay, 523 is this. So now compare this line and this line. If we subtract the two, what do we have? If we subtract the two, well, there's this common factor, first of all. No? There's a common factor here. He seemed to be heading towards a non-commutativity of covariant derivative, at least in the long run. I don't know this text. That's fine. That's fine. I mean, I put the link in the, I mean, not the link, but the name in the chat. I strongly recommend you, my viewers, to go check it out themselves. Just while watching what I'm doing, go check out the text themselves. I know this is a demanding request. Well, if you're here, I mean, I kind of assume that you want to struggle with me. So I'm sorry if this is not what you're looking for, because I'm not completely sure what is going on either. But basically, this is what we follow. From what we follow so far, we have these two. Okay, and we're supposed to do subtraction. We're supposed to do subtraction, and we want to see what's going on the right. I think we should substitute a bar. This way I can factor out the Jacobian to the n. I think this is what what we're supposed to do. Otherwise, how can we proceed, right? So I think we're supposed to use this substitution here. Let me put that in green. Substitute this on the right. Okay, and see what we're going. See, this is, well, you got n dx over dx bar determinant to the n times a gamma sigma alpha sigma dx alpha over dx bar j. You know what? I really wish, I mean, just a writing saying, I really wish the author put his central message in the beginning of, say, an example. I really wish they do that. But I mean, I'll do that myself if I write a book. But I really wish they do that. Okay. Once again, I'm not trying to criticize. Okay, it's just that I understand writing a math book is an extraordinarily demanding task. It's not like writing a novel. I mean, writing a novel can be hard, of course, but writing a math book is much, much harder. And sometimes maybe this is what clicks for the author, is what it clicks to them. But I would rather they put the central message, the punchline, so to say, at the start. Because this is still a bit murky. All right, so let me just put 5, 2, 3 side by side with what I just obtained. All right, and see. Okay, this is 5, 2, 3. So subtraction will give us what? Subtraction will give us what? So on the right, we have, is there any common factors at all? Is there any common factor, anything at all that is factorizable? Well, here, let's just look at this term. Change a different color. This one and this one. Any similarity at all? Well, you got the common factor of the Jacobian determinant to the power of n. Yeah, that's something in common. Nice. And then you get the common factor of the transformation Jacobian, dx alpha over dx bar j. All right, so let me just put it here. Okay, so this is a green. Put it in green. If it's in green, it probably means something that is already derived earlier. I'm just put it on the side so that it's easier to compare things. So subtract (523) by claim times NA bar. Yeah. Yeah. So it's okay. It's okay. It's like I made a video much earlier. I was saying that when we learn a subject, we should adopt the mentality of a detective. We don't treat any textbook, any source, any paper as the ultimate source, but rather as, eyewitnesses of an event. So this way, in the process of gathering information, we can form our own story. Not our own story, but our own account of the event. So that's the idea. We don't expect an eyewitness to be completely coherent. Sometimes they forget things, but they do give valuable information. So that's what I'm trying to say. This is part of mathematical maturity. You stop looking for a singular source, the definitive account, and instead you treat textbooks, papers, and videos, lecture notes, whatever source, as potential informant. So here we subtract 523 by the claim times NA bar, we get the following. On the left hand side you get dA bar over dx bar j minus NA bar big gamma bar. And don't worry, actually guys, we will look at a more so to say, I remember Professor Pavel Greenfield's text to be a lot friendlier. So I'll just grind through this section, hopefully, because there are some rather non-trivial examples going on. But we'll try to, first of all, I'm just going to finish this part. Okay, I'm just going to finish this part. I'll transition to Greenfield's text and see what they have to say about what he has to say about covariant derivative, and perhaps we can extract some kind of new insights. Okay, other than, well, this is the algebra, it works. Okay, so we do the subtraction. Let me just finish that real quick. All right, so you have the common factor dx over dx bar, determinant to the nth power. Okay, cool. And then you have dA over dx alpha minus a here n a big gamma sigma alpha sigma. Okay, and then times the transition, whatever you want to call it, the Jacobian dx alpha over dx bar. Right, no worries. Enjoy your dinner, Steve. Thank you very much for stopping by. And dx bar j, so that's the first term. And the two, miraculously, I think that the last two term cancels. Right? Is that so? I think they, do they cancel? Here, this one and this one, they cancel. Yeah, I think they do. Magic happens, they cancel. So, yeah, they canceled out. So, yeah, this is what you have. So basically what it's getting at is this new combination. This combination here is a tensor. Yeah, this is a tensor. Wow. This is crazy. So this is a tensor. We managed to construct the tensor with weight n. And that is also covariant. Yeah. Oh, hi Leo. Thank you very much for joining the stream. The term, yeah, they freaking canceled. So, okay. So let's just say, okay, even though this algebra looks miraculous, can we at least compare this with how we constructed the covariant derivative earlier? Right. So here, from one miraculous derivation to another, basically. So in the first derivation here, the first derivation, this one, and this is the second derivation. We started, in the first one, we started from a, no, actually not this, this is not the beginning of the first one. Beginning of the first one is here. Okay, we started from an absolute covariant vector, its transformation law. And we take the derivative and figure, oh, it's not a tensor. So this is still very natural. The goal is to construct a tensor out of this. Right? So the goal is to create a tensor out of it. And for motivation that is still unclear to us, we decided to look at the transformation law of the Christoffel symbol, aka 520. Multiplying the Christoffel symbol, the transformation law of the Christoffel symbol, by a bar alpha, that is the new component of a. All right, and then we subtract 519 times 520 times a alpha, and what happens is the miraculous term, the second derivative term, cancels. I think if we treat that as our primary motivation, it kind of makes sense, right? Because I remarked that, oh, the situation with 519 is a lot similar to the transformation law of the Christoffel symbol. I remember saying that. Why? Because then there's an extra second derivative term. Right? The whole reason that it destroys the tensor property, the whole reason that the ordinary partial derivative isn't a tensor is because you got this second order derivative at the end. So what else have a second order derivative at the end? Well, it's just the Christoffel symbol. So let's do some funny business with the Christoffel symbol so that the second order term, the second order derivative cancels. So that's the motivation, right? See, yeah. So that's the motivation. So we have from that, because the second order derivative cancel, we managed to construct the tensor. It doesn't seem that miraculous now. So we're making some progress. Okay, even though we still don't know the geometric meaning of this new tensor. Unclear, totally unclear now. But at least the algebraic motivation is clear now, right? Second order derivative due to the product rule generates a second order derivative. Partial derivative of a product due to the product rule generates a second derivative term. Remember, this is what happens in the Christoffel symbol as well. So let's do a combination of the partial derivative and the Christoffel symbol so that the second derivative term disappear and you construct a tensor from the process. Okay, so this is how you construct the covariant derivative for a covariant absolute vector. Right? So that's the process. And now let's look at a different object that is a scalar, a rank 0 or order 0 tensor with weight n. Right? And once you have that, let's first write down the transformation law, just like here. We start from the transformation law. You take the derivative. Oops, because of the product rule, they're derivatives. They're the second order derivatives happening. And this is what happens. So you have, so basically, you need the second derivative. And here we use the identity we derived like days ago from the very first section. Not the very first section, I think section 3, but day 1. Right? So you can express the derivative of the determinant, the Jacobian determinant, in this way. Okay? Especially in the crucial observation is that it also involves the second derivative. So motivated by that, we're going to do some more funny business with the Christoffel symbol. Okay? And here, to use a Christoffel symbol, what else should we use? Here, we didn't use the transformation law of the Christoffel symbol itself, but rather we used a contraction. This is also quite ingenious. Let's see why. This is 523. This is 523. So in the Christoffel symbol, the transformation law of it, here, 520. How many free indices we have? Oh, there's 3. You have 3, alpha ij. There's 3 free indices, both in the first term and the second term. And there should be just one free index. If we're to cook up a tensor, or in particular a covariant vector from 523, the result should be a covariant vector. That is, you only need one index. So that's why we consider a contraction in the Christoffel symbol. So there's only one free index. Right? And then you multiply by n bar, n a bar. Why? Because here in 523, in the second term, you got an n a bar. Yeah, that's basically why. Yeah, that's basically why we got an NA bar. This is A bar. 2 together are A bar. Yeah, so to cancel that out, yeah, you do this business and they cancel. So it's not that miraculous anymore. But still, the geometric meaning of this newly constructed tensor, or in particular covariant vector, is unclear. We don't know what this is about. Okay, so that's very interesting. So let's just denote this as A bar, because A bar on its own has no index. So let's just write A bar comma j, and this is a comma alpha. Okay, so therefore this way you have definition. So you got a bar. Guys, I'm not reading chat. Okay, I'm trying to summarize what we just did. All right, dx over dx bar. Because I got comments from my videos and then say, oh, how do you know you should do this? Doesn't matter how smart you are. If you've never seen this, you'll never figure this out. All right, I think that's fair criticism, and a lot of math books do seem to be like that. And whenever that's the case, it's usually because of some kind of scratch work. Okay, scratch work for the proof, for the derivation is omitted, and only the final product is presented. Which is, to be fair, the standard of mathematical writing, but it can easily make reader feel frustrated. So anyway, perhaps there should be a cultural change in mathematical writing. This sort of writing style was very much pioneered by Gauss. Back in the days of Euler would put a lot of intuition, motivation, sometimes even erroneous attempts in his paper, and say, okay, I tried this, it didn't work out. And Euler did that. But when it comes to Gauss's paper, Gauss would just write, okay, this is how I do X, Y, Z, perform a bunch of magical steps, and finally, boom, a beautiful result appears. They're usually very short. This is Gauss defended his style by saying a respectable architect should leave the garbage, should clean up the garbage after the construction of a building. But if the point is to teach others how to build a building, that wouldn't be terribly useful, right? It's just like archaeologists to this day wonders how was the pyramid built, right? Because they only see the finished product and not the process. Right? Here I'm trying to recover the process, right? And the principal motivator for doing the algebra steps we performed earlier is to cancel out the second order derivative generated by the product rule. Right? And for that, the Christoffel symbol gives us that tool, because the Christoffel symbol transformation law, for the Christoffel symbol carries a second order derivative. So whenever you need to cancel out the second derivative, right, multiply the Christoffel symbol transformation law by appropriate factor, and then you just cancel it. So that's what we have so far. Even though algebraically this makes sense, it is still unclear what this special combination is about. Right? All right. So there's that. This is a relative covariant vector. Right? This is a relative covariant vector. So, and it is called the covariant derivative. Here, this thing and this thing are both called the covariant derivative. And the covariant derivative is a tensor. In this case, it's a relative tensor of weight n. Okay, so that is to say, a scalar of weight n taking covariant derivative becomes a covariant vector of the same weight. All right, so let's just give that a name. This is definition covariant derivative of the relative scalar. Relative scalar A. Now once again, if we're talking about Cartesian coordinate, the Christoffel symbol cancels, and it coincides, it reduces or collapses, degenerates to the ordinary partial derivative. Okay, guys, why do you retract messages? I still plan to read them. Just because I'm trying to make sense out of the textbook. I need to concentrate from time to time. Okay, it's not like I'm not reading your messages, but it's okay. It's your choice. Okay. All right. So let me just go back to chat and see what people are saying. Thank you very much. I mean, this is very complicated derivation, and still there's over 10 people watching. Thank you very much. I didn't expect. Usually because, when you start a new series, there tends to be a lot more interest. Over 2,000, 3,000 views per stream. But as the series progresses, because of the level of difficulty increases, it's natural that the views drop down. Okay, it's not a criticism of my viewers, not at all. It's just that, for example, to follow this, you need to already understand all those preliminaries, right? This is preliminaries, and these aren't easy. If you need time to digest those, that's totally understandable to me. These are just preliminaries before our goal. Okay, and there's still over 10 people watching, so that's amazing stuff. Okay, anyway, let me. So here I was just saying that people were saying that terms cancel. Yeah. Okay, so Ego, you were talking about learning the basics of tensor analysis and real analysis over the course of next year. I think that's totally doable. Think about, I only started this since when? Here, it's on the log here. This is like my diary. This is my mathematical diary, okay? Since when? Since, well, it's July the 23rd. That was how many days ago? Exactly 2 weeks ago, I started the tensor series. And guess what? We're deep in the territory of Riemannian geometry, albeit from a non-rigorous informal viewpoint. And there's nothing wrong with that as a first exposure. So this is actually tremendous progress, if I do say so myself, right? Of course, this is just the first exposure. You still need exercises to reinforce your understanding. But I'm saying is, if you give yourself a whole year to master this and you plan things right and plan things nicely and stick to them, I don't think that's unrealistic. Same with real analysis. I'm pretty sure you can study the first 7 chapters of Baby Rudin in a year. It's totally doable. So you can get very far. Not an expert, but definitely just the fundamentals. Just the fundamentals. The thing is, nobody learns real analysis in one go. Okay, guys, I still learn new things from linear algebra. It sounds a little bit perhaps surprising. I took linear algebra well over 10 years ago. And of course, nowadays it's over the years I've seen other texts, other expositions, new problems, and I get new understanding of linear algebra still to this day, let alone real analysis, right? So you can't expect to become an expert, but rather you will recognize the important notions in real analysis, right? You will, for example, you aren't intimidated by epsilon delta proofs anymore, and that's actually a great progress, right? And this is actually entirely self-motivated, which makes it even more valuable, because you aren't forced to take a particular course. When I was a applied math undergrad and stats undergrad, I took real analysis because I was forced to do it. Right? If I don't take it, I can't graduate. And as an applied math major, I hated real analysis. It just seems totally unrelated to other things I'm doing, or at least it feels like splitting hairs. If I can do the calculations, why do I need all those proofs, right? And actually, that was a great mistake. As it turned out, that I probably benefited from real analysis more than anything else I took. Right? So, um, yeah, it's really something that it takes time for you to see the payoff. And too many beginners, they give up at the early stage. That's just how things like in many aspects of the well, just anything, right? Like in learning an instrument. Like how many times do you see a person try to pick up say a guitar and played it a week or two and decided, oh, it's not for me. It's the same with math. Yeah, planning and discipline is the key, exactly. Yeah, so good for you. Good for you. Yeah, planning and discipline is indeed uh, slow and steady. What it says is this slow and steady, and I forgot how to say it. Okay, English not my first language, but let me just search that real. So slow and steady wins the what? Wins the race or something? Yeah, slow and steady wins the race. That's what I'm trying to get to. Yeah, working in a calm and regular way gets better result than rushing and stopping. Okay. Anyway. Okay. So, yeah, that's the two examples. Okay, the two motivating examples for the covariant derivative. One for an absolute covariant vector, and one for a what's that? A weighted here, a weighted scalar. So, inspired by this, because we were able to get the main logic of the derivation. So why don't we derive the differentiation rule, but for contravariant vector? Wouldn't that be interesting? Hang on, guys. I just wanted to get some water. I'll be back in a minute. All right, guys, I'm back. Yeah, I took many analysis classes: intro, real analysis, mathematical analysis, complex analysis, Fourier analysis, functional analysis, tensor analysis for myself for 7 years. Yep, sounds about right. All these things, for 7 years is totally normal. Totally normal if you spend 7 years on all of those things. Well, I spent, oh dear. After limits in the Russian style, I was expecting derivatives in the Russian style. Guys, am I still alive? Am I still... The stream is still on, right? Is it? I'm only over 20. God, I feel small. Guys, is the stream normal? Because my OBS says it got disconnected. What's going on? Let me check my own app. Check YouTube on my phone. Okay. Okay, great. Okay, great. Yeah, it's still on. Anyway, okay, great. So I was saying that Wendelin, you're expecting derivatives in the Russian style. Actually, you know what? I think I'll do more Zorich. Yeah, I'll do more Zorich, so expect to see more Russian style whatever. Like tomorrow we'll continue with the Russian style complex analysis. Um, so it's not a joke. So Ego says, I'm only 20, I feel small. That's okay. That's okay. I mean, like for me, I say psychologically speaking, one of the greatest thing in studying mathematics is to feel small. Oh, yes, I do have cat. You're not hallucinating. Sometimes you hear cat noises. Well, if you look at my thumbnail, not thumbnail, but profile picture, it's me with a cat. Although that one passed away. Um, anyway, I have two cats right now. So, as I was saying, doing math do make one feel small. This is completely normal. Yeah, this is completely normal. I would say. Uh, I I mentioned it in my first PDE live and said that just the field of PDE is so small. It's so large. Sorry, it's so large that you can spend your whole life on just one class of PDE. It's a humbling experience. It requires you to put down your past achievement and face the concept, the new notion, the new problem as it is. Okay, none of your past achievement matters. It's just you and the problem. Is there something pure, something just ethereal of this experience? It's almost like a religious experience. Um, I mean, I'm a Christian and I pray to God, and in the process, you feel you're humbled, right, by the scripture, by the apostles, and all those things. When you do math, something similar happens. You feel humbled by the problem. Anyway, let's continue. So here, the bottom line is that okay, this is what the book says. This is what the book says, and it's a monstrous formula. Let me just write that down. It says, quote unquote, in general, if you differentiate a general tensor, you will not get a tensor, but you can cook up a tensor. That's the idea. In general, it can be proved that if T alpha 1, alpha 2, all the way to alpha R, these are the upstairs indices, and beta 1, beta 2, all the way to beta S is a relative tensor of weight n, of weight big N. Then what happened? Then this new combination, okay, this new combination, which looks absolutely horrendous, but basically looks like this. Okay, this is defined. This notation, first of all, is alpha T alpha 1, alpha 2, all the way to alpha R upstairs, downstairs beta 1, beta 2, all the way to beta S, comma M, comma M. So comma M, as what we established so far, this stands for covariant differentiation. Okay, and it is defined as following. This is the definition. Okay, definition. And here we come. It's a long expression. dt alpha 1, alpha 2, all the way to alpha r, beta 1, beta 2, all the way to beta s, over dxm. Okay, dxm, and then plus t t what? T mu alpha 2 all the way to alpha r. So we're replacing alpha 1 by mu. Okay, and then downstairs is still beta 1, beta 2 to beta s. These are unchanged. And then times the Christoffel symbol. Christoffel symbol, gamma alpha 1, mu m. So mu is contracted. Okay, so that's the first term. And then plus dot 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 all the way to t, the first row. Okay, this is still the first row, the second row. T alpha 1, alpha 2 all the way to mu. So we're replacing alpha r by mu. Downstairs is unchanged, beta 1, beta 2 all the way to beta s, times this gamma with alpha r as upper index and mu m as lower index. Woo! But that's just the first line, okay? And there's still, you have the the lower indices, okay? The lower indices are, on the right hand side, are T alpha 1, alpha 2 all the way to alpha r. These are unchanged. And mu, okay, mu beta 1, not beta 1, beta 2, okay, mu beta 2, replacing beta 1 by mu, okay, mu beta 2 all the way to beta s times the Christoffel symbol, gamma mu on top, beta 1 at the bottom, m, like this. So notice something. So for the upper index, the correction term are positive, and for the lower index, for the lower indices, the correction term has minus sign, minus all the way to t alpha 1, alpha 2 all the way to alpha r. Okay, and then beta 1, beta 2, hopefully you can see the pattern now, okay, all the way to mu, big gamma, hang on, mu, beta, sm. And that's not all. And that's not all, because we haven't taken into account of the weight yet. Okay, so for the weight, you need an extra correction factor, so it's minus n, with t indices completely unchanged, still just alpha 1, alpha 2 all the way to alpha r, and then beta 1, beta 2 all the way to beta s, and then times big gamma mu m. So the contraction happens in the what's called the Christoffel symbol itself. Yeah, that's a theorem. Then this thing, still haven't finished yet. Then this thing, right, define. This is the definition. This is the definition. It is a relative tensor. This is a relative tensor of weight n. Okay, of covariant order one greater, of covariant order 1 greater than the original tensor. So the purpose of covariant differentiation is to turn a tensor into a derivative of itself that is still a tensor. Okay, so this sentence is still not yet finished. Okay, then this monstrosity is a relative tensor of weight n of covariant order order 1 greater. Right? There's an extra index downstairs, so it's covariant order 1 greater than the original. And then T alpha 1, alpha 2, all the way to alpha r. Downstairs is beta 1, beta 2, all the way to beta s. And is called the covariant derivative. And is called the covariant derivative. Of the monstrosity T alpha 1, alpha 2, all the way to alpha r, beta 1, beta 2, all the way to beta s. Whew, we did it. Okay, that's the full statement. And in the middle of it is the definition of a covariant derivative of a tensor in general. Oh my goodness. That's the definition of a covariant derivative in general. Right. So instead of course, memorizing it is unnecessary. You just need to know what to do about each index. First, this is just the ordinary partial derivative. And you got all these correction terms, basically. Now, these are correction terms. So for the contravariant indices, the upper indices, we're going to replace the index one at a time by a dummy index. Say alpha 1, replace that by mu, and pair that with the Christoffel symbol, gamma. Right? Gamma alpha 1 on top to maintain consistency, mu downstairs to make sure mu is contracted, and m downstairs, once again, to maintain consistency. And you do this for all the upper indices. And for the lower indices, the process is largely the same, with one crucial distinction, namely, you put a minus sign instead of a plus sign. Okay. For the contravariant indices, the correction terms are all positive, and for the covariant indices, the correction terms are negative. And finally, you put an extra correction term to account for the weight, the big N, right, the weight. In which case, the indices in T are unchanged, and the contraction happens in the Christoffel symbol itself. So in general, it can be proved if T blah 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 is a relative tensor of weight n, then this monstrosity is a relative tensor of weight n. Same weight, but of contravariant order 1 greater than the original tensor, and it's called the covariant derivative. Okay? Hopefully we're on the same page. Okay. Let's read chat. Chat, what do you think of this? Oh my god, I feel my hand hurt just looking at this. I know, right? So I guess this should motivate us to learn about, say, the index-free or coordinate-free notation. Right? Just got sick and tired of writing this. But at least, well, this is one valid definition. Right? You can do calculation with it. But still, the geometric meaning is still a great mystery. Okay, just keep that in mind. Okay. Anyway, just want to make sure that we understood. Not understood, but rather, should we say, not understood in the sense that we intuitively grasp the meaning of it, but basically we wanted to replicate this derivation. So as an extra exercise, this is something extra. Okay, it's not in the book. Yeah, we need to pray to God to learn this. Now, I do that all the time. I literally, like, yeah. So, not to say, God, please make me smarter, because usually that's not the biggest problem. I ask for, I pray to God, so God help me so that I don't give up. Okay. Please give me courage so I don't give up when I'm frustrated, when I'm impatient. make me patient. Okay, so that's perhaps, in my opinion, more important than intelligence. Okay, so let's do an extra derivation. So now consider the contravariant vector. So let's consider absolute contravariant vector. Consider an absolute contravariant vector. Right? Say what would be the good notation? Say AI, right? A upper index I. A upper index I bar. Okay. Its transformation law should look like A alpha upper index, and then dx. This is contravariant, so dx new over dx old. I upstairs, alpha downstairs, like this. Okay, start from that. Right? We wish to derive the definition. We wish to derive the definition of the covariant derivative of this thing. Right? So our goal is to derive the expression for what's the expression for the covariant derivative? Well, you put a comma. So that's a bar I comma j. This is what we want. Yeah, this is what we want. Okay. Okay, so starting from let's give it a name. Okay, let's just use the Roman numeral 1. Starting from d over dj. Actually, d over dj bar, because that's the new coordinate. D over dj bar of 1. We get dA bar I over dx bar j, like this. Okay, cool. And then we use the product rule. Of course, it will generate a second derivative as expected. All right, so here, the first term should be what? Let's use the chain rule already. So it will be dA alpha over dx bar j, which we will write it as a chain rule. Okay, let's write as a chain rule to think about an index. Let's use beta, shall we? So let's dx beta, dx beta. And the second factor is unchanged, which is dx bar j, dx bar I. Yeah, dx bar I, dx alpha. Okay, and then by the product rule, should have a second term, which is a alpha. Okay, which is a alpha, and then the derivative of the Jacobian with respect to dxj. So should we use another chain rule to do it? I think we should. So let's write it as, so d squared, you need to differentiate this first derivative. You get a d squared x bar i, and dx alpha, that's already there. Okay, you now want to differentiate with respect to dx bar j, so you put a dx bar j here. Right, so get a dx bar j here, and let's do a dx beta here, and then put a dx beta up there. So this is just the product rule and the chain rule, okay, from 1. And of course, notice this is not a tensor because of the extra term. Okay, let's write it on the side. dA alpha over dx beta is not a tensor. Or should we say dx dAi? dAi over dxj is not a tensor. Okay, this is not a tensor. And how do we make the second order term disappear? Well, try the Christoffel symbol. Okay, where's the Christoffel symbol transformation law? Right here. That's the Christoffel symbol transformation law. Perhaps we need to change the index a bit to help us recognize commonalities. You know what? Let's just use this from the beginning. This is the Christoffel symbol transformation law. Right here. This will help us get rid of the second derivative term. Right, that's the algebra anyway. So looking at this, what can we do? So first of all, shall we change the indices a bit so make things easier to recognize? Yeah, let's do that. So first look at the term that we wish to cancel. Right, we wish to cancel the second derivative term. And in the second derivative term, what are the free indices? What are the dummy indices? Beta is dummy, alpha is dummy, ij are free. Ij are free. So let's rename the indices so that it looks pretty much the same. Okay. Here in the Christoffel symbol, we got three free indices, ijk, in the last term as well. Right, in last term as well. So hold on. Hold on. This doesn't feel like we can cancel, huh? Because this is downstairs. This is upstairs. What can we do? Earlier we have the coincidence, if you will. Here, in earlier part of the derivation, here, the second derivative term in the Christoffel symbol transformation law have x bars downstairs, which happens to be the same. Which happens to be the same as 519. Okay. And here, this is not quite what we wanted, because we have upstairs. This is upstairs. What can we do? X bar is upstairs. Well, we need to get rid of the. We don't want to put gamma bar on the right hand side, because this will mess up the. This will mix up new and old coordinates when you do the subtraction. This is not what we want. We want to keep the format as it is. But right now, here, this is not something that we wanted to do. What's the general hint here? We shouldn't even do a subtraction. We should add, right? According to the general result, if you're handling upper indices, the correction term should be a plus sign. Should be a plus sign. Why are we doing the minus sign here? We shouldn't subtract, right? That's the idea. But how do you because this is x bar is upstairs. We don't want that. Let me just double check this line. dA bar I over dx bar j. This looks okay. It doesn't match, huh? Yeah, it doesn't match. Oh, hang on a second. Is this right? It's a covariant vector. It's a covariant vector, so that's the transformation law for the covariant vector. Let me just double check. One should be correct. 1 is a covariant vector. A bar I is a alpha times dx I bar over dx alpha. Yeah, that's correct. Differentiate with respect to dxj. You see, I'm supposed to multiply this. I'm supposed to multiply this. Actually, you know what? Let's just follow this. Follow the general recipe here. So what is said is that I'm supposed to, okay, I am supposed to do this. dA bar I over dx bar j. Okay? And then plus a bar, the upper index gets changed to say mu, right? So say mu. A bar mu, yeah. And then gamma, follow the recipe. Or recipe, it should be I on top, mu j at the bottom. So I need to show this is the tensor. Oh, new Christoffel symbol as well. So this should be a tensor. Okay, so let's just substitute everything in, shall we? And hopefully things works out. We just have the differentiation formula here. So let's put that down. This is what we have. Or perhaps I shouldn't do the chain rule, huh? Is that fair to say I shouldn't do the chain rule? Perhaps I should do the chain rule in the first term. I need the chain rule in the first term. Because I need dA old component over d old coordinate. If I don't use the chain rule, you will get dA old component over d new coordinate. That's awkward. So I need dA alpha over dx beta. That's my point. That's why I need this chain rule here. I need this term. Okay, so that seals the first term. However, for the second term, do I really need the chain rule to write the partial derivative that way? Let's take a look at what we did earlier in the first derivation here. Here I didn't. I didn't cook up a new chain rule. Is it because it's unneeded or something else? Right? I don't know. But here in the second derivation, I deliberately wanted to have both bar coordinate on the second derivative. I wanted that. Right? I expressed this determinant purposefully as a second derivative with x bar, with two x bars at the bottom. So I figured I shouldn't probably do this. Perhaps this is a mistake. Well, not a mistake, but not an ideal move. So I'm saying is, when using the product rule, right? Using the product rule, you would first get dx bar I over dx alpha, and you want to differentiate it with respect to dx bar j. What can you do there? What can you do there? Well, if you don't do what I just did here, then you would mix up new and old coordinates again, which is awkward. I really don't know what better thing I could do. Okay, so basically, if I don't use the chain rule, it would be like d square x bar I over dx bar j dx alpha, which is awkward because you're mixing new and old coordinates. I would rather prefer all new or all old downstairs, so that's why I did this. Right? D square x upstairs, d square x new upstairs, so dx old downstairs. So this is what I wanted, but it does not conform to the transformation of the Christoffel symbol. That's very disappointing. But let's not be completely demoralized. Okay, so let's just keep on substituting and see if good things happen. Okay, so a bar mu using the transformation law would be a alpha, or a alpha. Is that a good idea? Perhaps not, huh? Perhaps not. Perhaps not, because this will alpha is already, yeah, alpha. Yeah, we can use a alpha here. That's okay. A alpha dx bar mu over dx alpha. Right? This is a bar mu. And then times the formula for the Christoffel symbol. Okay, so you get big. Okay, so first gamma I mu j. Okay, so let me just set up the structure first and then worry about the indices later. And then the second derivative term, once again, worry about the indices later. Okay, and then dx bar over dx. Okay. So here on the left, we got free indices I mu j. And let's check where the free indices appear in the second term. Okay, I should be up here. Mu j are down here. And sigma here, sigma here. Okay, good. Okay, good. So, and what else? I up here, mu j are down here. Mu j are down here, and then do the dummy indices. Do the dummy indices. Which dummy index should be used? Alpha is already used. you know what? I'm gonna change alpha here to say something else. I'm gonna use say new or row. Let's use row. A row dx row. And in big gamma, let's use alpha on top. So there's alpha down here. Beta, beta, gamma, gamma. Okay. Whew. All right, so that's the new Christoffel symbol, the transformation law of the Christoffel symbol. Okay. Okay, can we simplify this? Perhaps some kind of shenanigans with the Jacobians, huh? Yes, indeed. Yes, indeed, because this term right here and this term right here gets combined to a Kronecker delta. This is delta beta rho. Beta rho. So A rho becomes A beta. This is promising. So A beta times the Christoffel symbol gamma alpha beta, gamma alpha beta little gamma. And what about these two? The remaining Jacobians. Okay, let's just do things a little bit slowly, okay? So here, combining the first and the second term, putting those two terms side by side, okay? So you have dA alpha over dx beta over dx bar j times dx bar I over dx alpha, and then plus A beta, and then gamma alpha beta gamma. Okay, and the two Jacobians remaining is dx bar I over dx alpha and dx gamma over dx bar j. Okay, so comparing these two terms, we haven't even touched the last two terms yet, but based on these two terms, we notice something. So this is a common factor. They're the same. Are they? They're the same, are they? Well, actually, we need to do something to reveal that. Okay. Here, gamma is the dummy index, so let's change gamma to. Can we change gamma to beta? That wouldn't be a good idea because the beta is here. This beta here. So let's change beta to something else. Let's change beta to let's change beta to mu. Okay, change beta to mu. Change beta to mu. Change beta to mu. Change gamma to beta. Change gamma to beta. This way, the Jacobian terms are the same now. Dx beta over dx bar j times dx bar I over dx alpha. So now the two terms can be combined into dA alpha over dx beta plus A mu plus A mu Yeah, plus a mu gamma alpha on top, mu downstairs, and beta. Together multiplied by dx beta over dx bar j times dx bar I over dx alpha. Okay, so this is promising, you see? And it would be nice if the last two terms cancel. We still haven't touched this thing yet. We still haven't touched this thing yet, but hopefully they cancel. Is that possible? Let's see. Is that possible? Because if this is what we want, then the two term at the end should cancel. And this is where we were suspicious, right? We were suspicious. Oh, you see the second derivative term, they don't have the same format. So I don't know. Like here, if we look at what's going on in the second terms, the second and the fourth term, well, here you have A alpha. Nothing you can do with this term. Nothing. But here, A alpha, A rho, say A rho times, yeah, I'm just using the definition of A bar mu here. Yeah, A rho times dx bar mu dx rho. Hold on a second. Where did rho go, huh? What the F? Oh, rho. Actually, rho is here. Rho is here. So mu should do something with this term here. Okay. Looks like chat is chatting among themselves. Oh, Leo, you're talking to me. Sorry. I was just doing this derivation. So here, Leo, give me a link. It's his blog. Hang on. My first high effort. High effort? What do you mean? They all look high effort to me. Yeah, it's my first high effort YouTube video. With some luck, well, you're too modest. This type of historical and philosophical math video essay was always what I wanted to put on the channel. I have many other videos and earlier works. A large project. Okay. Yeah, this is an insane amount of work. My goodness. Yeah, this is crazy. You see, I don't do music at all, so that saves me work. But definitely. Perhaps I should do music. I don't know. What do you guys think? I don't do music. It's just I'm too lazy to think about, okay, what sort of music should I put? I have no idea. Yeah. Yeah, Leo, if you don't mind, maybe you could tell us a little bit about yourself, like where did you get your education and how did you get into mathematics, that sort of thing. But I mean, it's totally up to you. You don't have to. I mean, I always kind of wanted to de-emphasize sort of formal background, formal education, I don't mean it's unhelpful, but because I find it in real life, people are quick to judge others. But I mean, if that's something you wanted to not share, that's totally okay. Your content is speaks for itself, so I don't find a particular need to for you to disclose it. But if only if you want. Okay. So anyway, so here we have the interviews. Dario Bini. This is okay. And actually, because I have to read this in more detail. Okay, sorry guys. I if you wanted to want me to read Leo's post in detail, unfortunately, currently this is not what I'm planning to do. I'm trying to focus on understanding the covariant derivative. But yeah, Leo's new videos, actually two of them, were just extraordinary work. I learn a lot. I have to constantly pause it and look things up. I mean, I suppose that's a good thing. Yeah, I suppose that's a good thing. There's so much information in there. Okay. Yeah, you made the music. Damn, bro. Yeah, this is why I'm just too lazy to do music. I just figured, oh, I'm just so tired, man, with the editing and whatever, the math content. I just wanted to get it over with, put it out, okay. But music can help. Yeah, 3 days after you posted your main video, you did your update. My goodness, this is great. This is great. This is like a diary of a creator. Awesome. Yeah, don't overdo it. Don't overdo it. I mean, you want to keep things sustainable, right? Oh, okay. Um, you also put less time into streaming. Um, yeah, in research and academic. So I suppose yeah, accounting house, exactly. Yeah. Yeah, so no worries. Yeah, so I mean, anytime you want to come back, then please do. You know what, guys? I don't know how busy I'll get in the next month. I mean, this month, and the previous months were very much the anomaly for me as well. Hope you feel better, man. Yeah, health comes first, always, as always. Yeah, awesome. Thank you so much for sharing your workflow and your journey. This is awesome. I'll read this in more detail later. Okay. So, um, yeah. Sorry, it's 4 a.m. and my brain is failing me. I know, right? It's failing me too. I don't see why the two terms at the end cancel. They're supposed to cancel. They're supposed to cancel, no? Yeah, they're supposed to cancel exactly. Unless I did the thing wrong, which I don't think I did. So for some reason, their things are not canceling out. Okay, I know, right? So here I was saying, still have to watch the category theory stream. Yes, please take some time out of vacation. Like, what do you mean you're a high school dropout who finished 0 semester of high school? I don't believe it. I'm sorry, Leo, but I don't believe it. Okay. Anyway, that's okay. Now put pictures of fighter jets somewhere in every frame of a video to capture and hold attention. Yeah, it is. I mean, I don't think like your earlier videos are low effort. Like, you know what? Your first video, I think axiom versus assumption, right? That's not low effort, not by any means. I mean, I definitely put out low effort videos earlier. I think all my book review videos are so low effort, man. It's just like flipping the pages and say a thing or two about a topic and just kind of name dropping along the way. I figured that's low effort, so I stopped doing it. It's feel unrewarding to me. It's like just it's like farming views, man. And um, I don't know. Um, if it feels like I'm deceiving myself into thinking, oh, I'm pretending that I know all of this, but I really don't. So I stopped making book review videos. Yeah. Anyway, so coming back to this derivation, how on earth does this one and this one freaking cancels? If the content is good, the problem is not good. Like in retrospect, I don't think like many of my videos, especially book review videos, are good. That's the thing. It just feels like I'm not talking about anything substantial, and the format is intrinsically limiting. So I just stopped doing it. Okay. You know, like it's not. Think about it this way, okay? So if let's say if think about a factory owner or a businessman, like or just a business owner, right? Not everything you do needs to be high cost, but you do want to make sure it's high quality. Right? High cost on its own is not a merit, just like high effort on its own is not a merit. Right? I just find perhaps I use the term, say so-called high effort or slash low effort is because I find some of my older content to be low quality. Like I didn't really say anything in the say one of my book reviews, some of my book review video. I just kind of flipped the pages and dropped names and didn't really. I don't think it's helpful for anyone who reads the book or first to watch the video unless they already kind of know the subject, which is kind of defeats the purpose of a book review anyway. Right? If I say, okay, this is the best book for a beginner, and or I'm just saying, okay, why say a diffusion equation is important for stochastic processes, like this, of course, you as a beginner you will get completely confused. That's totally normal, and I don't think that's very helpful, and so that's why I don't consider it to be high quality, not just because it's low effort. If you anyway, I mean, don't be reluctant. I'm very opinionated. Okay, so sorry, Crucial. If you wanted to do book reviews, it's not the intrinsic. I mean, I've made it sound like it's because of the intrinsic format limitation. But do feel free to share. Like if you find a rare book, if other people don't know about it, then perhaps it could be helpful. Like it's just for me that I find it to be a little bit. I don't know. I perhaps it's just me watch too many book review videos. Yeah. Sorry. Yeah, Crucial. I didn't mean to discourage you from doing that. It's just I kind of I no longer enjoy making them, and I don't just because I don't think I'm able to put out high quality book review videos anymore, so I just stopped doing them. But that doesn't mean it's the same for everybody. Okay. Yeah, some old rare books out there. Yeah, and sometimes I do recommend things like in the format of my. Hold on a second. What's going on, guys? Yeah. Oh, actually, did my screen went black for a second? Yeah, from the old Soviet Union, and and that's like that. So it's good to. I figured if I want to do a book review or recommendation, I would just do it in the post. I'll just do it in the post and say just perhaps one line or two about it, and not a full video. But that doesn't mean no one else can make interesting content from it, right? So anyway, guys, I'm really struggling to see why these two terms cancels. Can someone help me out here? Okay, because hold on a second. It says low quality, huh? Warning. There's a warning. Guys, this is my OBS and it says there's a warning. The stream is what? The stream is lagging? Is the stream lagging? Um, that's okay. That's okay. I think at this point I want to check the AI. Check with the AI. How do you derive the definition for the covariant derivative? Okay. Yeah, just recap the last 20 minutes. We're trying to show a derivative of a tensor. That's right. And I wanted to show, in particular, I want to verify this definition. I want to show that in the case of a contravariant tensor, this construction will give us another tensor. Remember, in the main text, we did the covariant derivative of a covariant vector, absolute covariant vector. And we showed that and we verified the covariant derivative of a scalar. But we never tried the contravariant case, that is the upper index case. We never did that. So that's why I wanted to verify it, but here I cannot get this right. Yeah, okay, great. So now the quality is back to excellent again. So here, there was a warning. Now it's excellent, so it's fine now. So I think what I'm going to do now is I will try to describe my problem to ChatGPT. I have the cheapest version, the free version, and we'll see how it turns out. Okay, so our goal, that's right, our goal is to derive the coordinate expression for the covariant derivative of a contravariant because typing LaTeX is not really fun here. I'm just going to describe things verbally. The covariant derivative of a contravariant vector in tensor analysis. Okay, so consider a contravariant vector AI. Okay, so start from its transformation law. Okay, I'll write down the transformation law so AI at least are with us on the same page when it comes to notation. So that will be AI bar equals A alpha. Yeah, this is LaTeX. And then you got dxi over dx alpha, so partial xi. Okay, and then partial x alpha. Partial x alpha. So that's basically the transformation law. Differentiate with respect to the transformation law with respect to x bar j, the new coordinate. X bar and upper index, yeah, make sure it's the upper index, x bar j. Okay, then use, okay, then consider the transformation law for the Christoffel symbol of the second kind. Christoffel symbol of the second kind. Our goal is to show that the combination of dx dai partial, maybe do a fraction partial ai over partial xj, yeah, and then plus. There should be a plus sign, but I wasn't able to see how it works because the second and the fourth term don't seem to cancel. So now let's say a mu, and then a gamma, yeah, big gamma, superscript I, lower script mu, and j is a tensor. Okay, so that's our goal here. Let's see. This is a classic derivation of the covariant derivative of tensor analysis. When start from the transformation law of a contravariant vector, differentiate it, observe the appearance of unwanted second derivative term, and show that adding a Christoffel symbol exactly cancels it. Right? That was the strategy. That was the strategy. Let's see the execution here. Okay, so this is the change of coordinates. That's the transformation law. Repeated indices are summed exactly. Okay, differentiate with respect to the new coordinates. Okay, let's see. Are we using the chain rule here? Yeah, this one here, this box equation looks exactly like the one we had earlier, right? This one here. Do we have dAi bar, yeah, over dx bar j, yeah, dA alpha over dx beta over dxj times dx bar j over dx alpha. So we nailed the first term, excellent. The second term, we got A alpha here, yeah, as the same as I did, right? Same as I did. I wanted to put the denominator, if you will, to be all lower, so we not lower, or old coordinates, dx squared x bar I, dx bar dx alpha times dx bar over dx bar j. Okay, excellent. Notice the second term, if the only first term were present here, if the only first term were present, the ordinary derivative would transform tensorially. The second derivative of the coordinate transformation is precisely the obstruction. Okay, we want to get rid of this thing. And here we have the Christoffel symbol transformation law. Exactly. So in the Christoffel symbol transformation law, which we also repeated here, right? The crucial thing is that in the second derivative term, we have new coordinates downstairs in the second derivative here, exactly as we wrote here. But as I was saying, the issue is that this is not quite the same second derivative we have earlier. In our second derivative, we have old coordinates x bar downstairs. So how do we remedy that? Right? How do we? Okay, so let's compute this. Let's compute the product of A bar mu and gamma bar. Yeah, this is what we're trying to do as well. Sorry. This is what we're trying to do. Here in our notes, right, we try to calculate a bar mu right here, this line. Trying to calculate a bar mu times gamma bar I mu j. That's what we want to do. Okay, we substituted the transformation law. Okay, here it uses lambda, I use rho, same thing. Okay, multiplication. Okay, so let me just zoom in a little bit, perhaps like this. Okay, so for the first term here, the first term, a lambda dx bar mu over dx lambda, the same as what I have here, times the Christoffel symbol, gamma alpha beta, yeah, and the three Jacobians. Okay, dx bar I, dx alpha, dx beta over dx bar mu, dx gamma over dx bar j, exactly the same. Even the dummy indices are the same. But notice that here you got dx bar mu over dx lambda, this term right here, with dx beta over dx bar mu, you get the Kronecker delta exactly. I did that. So the first part simplifies, yes. The first part, yeah. So the first part simplifies to a beta gamma, big gamma Christoffel symbol, big gamma alpha beta gamma times the two Jacobian. Hang on a second. Yeah, that's right. This is right. And the second part, hold on a second. Second part, second part we don't do anything, right? Here, the second part is a rho. Yeah, he uses a lambda. Dx bar mu over d lambda. Yeah, it's the same thing here. Second derivative. Dx squared over d. He used rho. Okay, rho is supposed to be, yeah, rho is contract with this one, with one of the Jacobians, so that's right. Okay, mu j downstairs. Okay, so this checks out. This does nothing. Okay, basically does nothing. Okay, and now we add. Here comes the great mystery. Okay, so now we add. So now just reduce it to proving that the bracket quantity vanished, exactly, which I wasn't able to do. So how come this vanished, right? Because you got these two aren't the same partial derivatives. Coming back to the same old problem. Whoa. This is insane. How on earth am I supposed to come up with that? This turns out to be the partial derivative of the Kronecker delta? My goodness, this is crazy. Okay, so start from the identity, Kronecker delta. Yeah, it's just the inverse matrix relation, and then you differentiate with respect to the new coordinate. It turns out it's the same as earlier. You know, this. Are you kidding me? Are you kidding me? So what the hell is it? Oh. It just vanishes, huh? So boom. Okay. Okay. Wow. Okay. So, all right. So let's try that ourselves. Okay. So this is magical. What else can I say? Yeah. Yeah. This is magical. So apparently. Yeah, so apparently the key is to differentiate Kronecker delta. And then you can show the fourth and the second term cancels. My goodness, this is crazy. So, okay. So maybe let's do a change of index. Okay, so A alpha here, and then gets multiplied by d squared x bar I over dx beta dx alpha, and then dx beta over dx bar j. All right, and then plus here, let's change rho to alpha. That shouldn't matter, right? In the second, yeah, there's no alpha here, so we're fine. So we get dx bar mu over dx alpha, and then times d square x sigma over dx bar mu, dx bar j, dx bar I over dx sigma. Okay, check the indices. Okay, the only thing free should be j, or ni. Okay, I and j should be free. So which means in this bracket, alpha ij should be free. Okay, so the first term looks fine. Beta is contracted. In the second, mu is contracted, sigma is contracted. Okay, so that's cool. So it remains to show that this is 0. So let's give this a name and call it star. And we claim that star is 0. We claim that star equals 0, okay? Yeah. So it says we start with differentiating the Kronecker delta. So let's consider, okay, so this is, what is the structure of this, okay? What is the structure of this? We have, so it should be some kind of a product rule. It should be some kind of product rule. That's what we're trying to get to. So maybe start with, say, dx alpha over dxi bar times dx bar I over dx beta equals the Kronecker delta, right? So that's an identity, and let's differentiate with respect to dx bar j. This is the inverse matrix relation. So basically it says these two are inverse matrices. The product is this has nothing to do with dot product or cross product. These are just inverse matrices. So this is one Jacobian, this is the inverse Jacobian, and the product should be the identity matrix, and this is just in component form. Okay, so dx bar over dj, okay, on both sides. Okay, dx bar over dj, what we get? Well, the first term, let's use the chain rule. Oh, no need for the chain rule. Just dx square alpha over dx bar j dx bar I. Okay, and then times dx bar I dx beta plus what? Plus dx alpha over dx bar I times, okay, d square x bar I, and you want to differentiate with respect to dx bar j, but you don't want to mix up. New and old coordinates. So let's keep dx beta here and dx bar j here. And you need a chain rule to accommodate that. So you need, let's say, dx gamma here, dx gamma here, okay? And this will be 0. Does it look like what we're trying to get at? Does it look like that? Almost, right? Almost. So I want to get rid of this thing here. So let's multiply that by inverse matrix. So multiply multiply this by d. I want to get rid of this thing. So let me get dx bar I on top, and d. Is there any unused Greek letter? There has to be. Let's say dx delta. Let's do that. Okay, so on the left you have dx bar I over dx delta, second derivative. Does this make you guys want to learn the coordinate-free version of tensors? Guys, after suffering through this derivation, do you guys want to learn the coordinate-free version of the tensor calculus? Question mark? This thing multiply that should gives you the Kronecker delta, alpha delta. Actually, delta is not a good idea because of the Kronecker delta. Let's use maybe use sigma. Okay, let's use sigma or lambda. Let's use lambda here, just like AI. Okay, now do this with polar coordinates for maximum pain. I'm doing this for general coordinates, actually. If it is polar coordinates, then a lot of the Christoffel symbol term will be 0. So actually, that's easier. We're doing this for the general case. We're still trying to derive an expression for the covariant, covariant derivative. Yeah, the covariant derivative for contravariant vectors, upper indices. So put a lambda down here, lambda down here, lambda down here, yeah, lambda down here, and these two terms remains. There's two factors the same, and then swap the lambda, right? Swap the lambda. Where on earth is that? Oh, I can't do that. I absolutely cannot do that. Because I is already contracted. This is nonsense. I made a mistake here. This is not right. So the free index is alpha. I want that thing gone. So I should multiply by dx alpha and dx bar. I can't do j now because j is free. Let's do a k upstairs. Okay, dx bar k over dx alpha. Okay, and now this is delta ki. Yeah, and now it's just delta ki. Okay, great. And then you can swap the I for k. Just swap the I for k, and this becomes second derivative d squared x bar k over dx gamma dx beta. Okay, is this the same as what we wanted here? I mean, the indices may not match, but let's just take a look at what is free and what is not, okay? So here, this term looks like this term. Check where the free indices are located. The free indices are mu. Yeah, the free indices are mu and sigma. Got it. So the d squared, yeah, alpha, this is contracted. Nice. Right, alpha here, alpha is contracted. This is what we wanted. And where else? So you need one thing on the denominator in the second derivative to contract with another first order derivative index. Do we have that? Yes, we do. I and I. Right? Here, this, that. Okay? So you're left with one I on top and alpha j at the bottom. So we have one k on top and a beta j at the bottom. So this matches the second term. Okay, and here in the first term, do we have a match? Let's look at the indices. Beta is contracted. Beta is contracted, and now we have what? Gamma is contracted. So up here we have K on top, beta and J downstairs. And here we have K on top, beta and J downstairs. Exactly what we needed. So this is indeed 0. So it's now shown. Is now shown. Yeah, yes, sorry, ego. I wish I could have explained it in a better way, because I was still struggling. I think the only way that a person can follow this while I'm doing this is simply to write the whole damn thing with me at the same time. Yeah. As I was saying in my PDE stream, I really wish to have kind of a, those 4 pieces of blackboards in the university. Guys, let me try to find it here. I was talking about this in my PDE stream. So I wanted to have like a 4-piece blackboard. In a university lecture hall. I'm not sure if you guys seen it. Yeah, something like this. But this is 6-piece. I was saying, like, if only I could have 4. Yeah, this is this one. That would be awesome. Because you often need to refer complicated expressions back and forth to tell what's going on. So now this is indeed 0. So we have verified this is indeed a tensor. Okay. So far so good. Okay, so far so good. This is, of course, purely algebraic. Everything we've done so far is purely algebraic. And it's still unclear what is happening geometrically. Okay, so let's see a different exposition. Here, let's see a different exposition. This is a website which I strongly recommend by Professor Pavel Greenfield. This is in the stream description. Professor Pavel Greenfield is also a fellow YouTube creator. This is his channel called Math the Beautiful. Did I subscribe? Yeah, I subscribed. Okay. Awesome channel. Unfortunately, he hasn't been posting for a long time. But yeah, he has his series of tensor calculus, introduction to differential geometry, tensor calculus. Yeah, go check out his stuff. And he has a textbook in print, but now he is rewriting it. Okay, he is now rewriting it. The book, this one, Introduction to Tensor Analysis and the Calculus of Moving Surfaces. Still, it's in the process of rewriting it, so I suspect it's the second edition of the book. But this is what he has so far. Chapter 4, differentiation of vectors. I suppose this is the Christoffel symbol, huh? The covariant, actually, chapter 15, huh? Chapter 15. Let's go here. The covariant derivative. That's Professor Pavel Greenfield's approach. So, our goal for this chapter is clear. Having discovered that the derivative of a tensor is not a tensor in its own right, we must look for a way to bring differentiation back within the fold of tensor paradigm. Okay? the solution will come in the form of a new differential operator known as the covariant derivative. Okay, we cannot really stress the importance of this enough. Actually, this is just me interjecting. Okay, we cannot stress the importance of this enough, because if we don't understand covariant derivative, we don't understand curvature. Is that simple? Okay, so this is the crucial ingredient that connects what we've seen earlier and the Christoffel symbol geodesics and the curvature tensor. Which is our ultimate goal, at least as far as this series is concerned. So the covariant derivative is a tensor, right, whose defining characteristic is tensor property, i.e. the fact that it produces tensor outputs for tensor inputs. Right? So that's what we've been doing. Right? We took covariant tensors, covariant vectors, covariant vectors, contravariant vectors, scalars, and feed them into the covariant derivative operator, and the result is still a tensor. And the result is just with one order higher in the contravariant department. Okay, in the covariant department, there's one more index downstairs. Okay, and it's still a tensor. That's what I mean. In the end, we will come to see the loss of the tensor property under differentiation, not as a setback, but as a welcome opportunity to broaden our analytic frame network. Okay, great. So here, in his notation, we use the prime coordinates for the new coordinates. Okay, so here it says, as we discovered at the end of the last chapter, if Tj is a contravariant tensor, see, Ti is a contravariant tensor. In this case, it would be contravariant vector, and also absolute contravariant vector because it carries no weight. Okay, so it's got one upper index. The transformation law for that would be Ti prime. That's the new coordinate, a new component, Ti prime. Ti prime. So prime coordinate is the new one. What did we say about contravariant tensor? Its transformation law would read like the old component Ti times the Jacobian, which is dx new over dx old. And this is the notation here. In Professor Greenfield's notation, he uses J to stand for the Jacobian. So this is Jacobian, and this this is Jacobian, which stands for dxi prime over dxi here. And then the variant is not a tensor in its own right because it transforms according to this identity exactly. Right? We just use the product rule. I just use the product rule. So the first term is now the first term, we're differentiating this with respect to dzj prime on both sides. Right? By a chain rule, you get the first term, which is this. We did that already. Okay, so let's just put things side by side with our own exposition here. This is a contravariant tensor, which is what we just did here. Contravariant vector. This is our transformation law, exactly the same as 15.1, slightly different notation. And then we differentiate right here. Okay? Still the same thing. Right, still the same thing. Two Jacobians here. And then, Ti, which we write as A alpha. The second derivative of the transformation. New on top, old at the bottom. Yes. Yeah, this is correct. This is completely the same. Okay. As a result, we do not see how the variant dti over dzj can be used as an expression that would produce the same value of all coordinate systems and would therefore be considered an invariant. So this is not an invariant. In other words, our analysis has lost its grasp on the geometric meaning. Okay? In order to restore the lost geometric meaning, we must reconnect our analysis to tangible geometric objects. Sure. Let's imagine that Ti is not some abstract tensor, but in fact a component of an invariant vector big T. And that the whole purpose of differentiating Ti with respect to the coordinates dj is to capture the rate of change of T. In fact, let us switch from the big letter T, right, the letter big T, to the letter U, which we commonly use for denote a geometric vector in Euclidean space. Sure. One thing though, we aren't dealing with just Euclidean space here. Perhaps this will give us some intuition, but I don't know about this step. Okay, but okay, just we're trying to follow the author. So switch the letter big T to the letter U to denote the geometric vectors in the Euclidean space. Once our present exploration suggests to us a way of retaining the geometric meaning in the course of our analysis, we'll switch back from U to T and extend our analytic insight to abstract tensors. Sure. Okay, so here, this is something that Professor Greenfield uses a lot in his videos, is to use basis vectors, which we haven't been using a whole lot. So the idea is we have a coordinate system, right, which coordinates zi. Then you can define basis vectors along the coordinates. So the zi's. These are the basis vectors. So the basis vectors are tangent vectors of the coordinate lines. Okay, but anyway, it doesn't matter. But if you have the basis vector, you can expand. You can do the basic expansion, just classic linear algebra, right? Einstein's notation doesn't work. The components ui times the basis vector zi gives you the full vector big U. And the big U is supposed to be independent of the choice of coordinate system. Okay, so recall ui and zi are both tensors. Actually, I don't know about zi, but perhaps just because we haven't been using basis vectors for at all, basically. So yet just treat it as given. Okay, let's just treat it as given. So downstairs, zi, this should be a covariant tensor. Okay. Furthermore, the collection of partial derivatives being the result of differentiating invariant is a tensor of its own right. Hold on a second. What's going on here? Sir, do you mean you're differentiating big U? If you're differentiating, actually, I didn't know about this, but let's just take that for granted as well. It says being the result of differentiating an invariant. So U is an invariant. If you differentiate an invariant, you get a tensor. Huh. Okay, I didn't know about that, but perhaps it's in the earlier part of the book. This is chapter 15 after all. So, okay, let's just take that for granted. With vector elements. Yeah, I suppose, because U is a vector, and each z is a scalar. It's not a scalar, but a number. So you get du over dz1, du over dz2, and so on. Right? Each component, each element is a vector, sure. And since you have, okay, this is just substitution, we should expect that analyzing the expression, okay, analyzing this expression, same as 15.1, huh? 15.5, huh? Yeah. Should present us with the insight we need for preserving the geometric meaning. Note that we're differentiating with respect to zk rather than zj, because we would like to save the index j for our upcoming analysis of second-order tensors. Okay, sure. Okay, use the product rule. Nice. They use a different definition for the Christoffel symbol. We use the Christoffel symbol as, you see here. This is interesting. In Professor Greenfield's book, the Christoffel symbol is defined as this. The Christoffel symbol is defined as the basis vector, the change in the basis vector, as a basis expansion. The change in the basis vector has a basis expansion. We didn't do that in our exposition. I don't even know whether this is true in general. I mean, the advantage of starting with a metric tensor is that you can forget about the vectors. Okay, you can forget about the vectors and just work with G intrinsically. But here, I mean, I don't know. Okay, guys, I don't know whether this is only true in Euclidean space or true in a space in a Riemannian manifold. Okay, or at least in the tangent space of a Riemann. I don't know whether this is true, but okay, let's just follow along. This is the alternative definition of Christoffel symbol, which arguably, let's say, if this is true in general, then it has a nice geometric meaning, right? So it measures how measures the rate of change of the basis vector. The Christoffel symbol. The Christoffel symbol is a measure of the rate of change of the basis vector relative to the old coordinate, or relative to the old basis. Okay, so sure, we substitute the last term, that is the rate of change of the basis vector. I still have to reconcile, okay, this exposition with our own. Okay, but let's just follow this. Okay, this is just substitution, fair enough. And then what else? Importantly, it says neither term on the right is a tensor, but their sum is. Right? Okay, so yeah, the sum is, we need to keep the two terms together. Both terms represent linear combination with respect to one and the same basis. We should therefore be able to combine them in a component by component manner. So you wanted to reindex things. Right, so M is contracted, so you rename M to I, so this way you can combine with the Zi. But then I needs to be renamed as well, so you change that to M. Just switching the rows of indices I M, this is what you get, and then you can factor out Zi. Since this Christoffel symbol is symmetric in its subscript, yeah, we know that. And this is what you get. And this is so you get a plus sign. This is how you get a plus sign. So this is a tensor in its own right. This alone should signal to us that this combination should take the place in the partial derivative as a differential operator measuring spatial variability. Besides being a tensor, the combination is decidedly preferred over the ordinary partial derivative because it actually represents the components of a derivative vector field. Actually, so I guess even though we still can't completely follow, because we define the Christoffel symbol a different way, but at least now we have a geometric interpretation of this quantity, which is nice. Right, so remember what we did here is purely algebraic. Right? Our entire concern in these derivations is that, I just want to cancel the second derivative term and create a tensor. But the geometric meaning is unclear. Here we actually have a geometric meaning. Right. So the vector U, the vector field U, is an invariant. The vector field U is a geometric object. It's independent of coordinate system. But now, suppose you have a coordinate system, zk. Suppose you have a coordinate system, zk, and you wanted to you want to see how the vector changes. Right? How does the vector field changes relative to the coordinate system? So let's draw a picture here. Yeah, actually we do have a picture right here. Yeah, this is the original picture that I drew. Yeah, so you have a vector field on the surface, right? And the surface has a coordinate system. You want to know how the vector itself, right? How the vector changes as the coordinate changes. So keeping all the other coordinates the same, and you vary zk. We want to see how the vector changes. And is what? And this formula tells us that it equals, this is the coefficient in the expansion. Right. So here, locally, you have a little basis for the tangent space. And this just tells you that this is the derivative of u. This is the derivative of u, and if you do the basic expansion coefficient are the covariant derivatives. This is very meaningful. So now suddenly you have a meaning for this. Suddenly you have a meaning for this. This is the expansion coefficient of the rate of change of a vector. The vector itself is an invariant. Here, like big A is an invariant. But if you go from, if you move along the coordinate line, the change of that vector is given by this expression. And in particular, this combination right here, right, is the expansion coefficient at the base of your consideration. So you're standing at a point, okay, with the coordinate, and zi is a basis for its tangent space, and d over zk, that's an invariant. That's an invariant, and here you get the coefficient for that. So basically, that's the meaning of the covariant derivative. The covariant derivative is, you can think of it as a collective object, right? That's a tensor. So that's a tensor. So basically, that's the covariant derivative of a vector is the derivative of a vector relative to the coordinate system. Okay, as a whole, not the component, because the component rate of change with respect to the coordinate is not a tensor. This is too much. Yeah, this is indeed too much. I mean, I know, right? Because perhaps it's very likely I'm not explaining it in the best way possible. Because, well, as I said, this is a very subtle concept, and I apologize for not doing, not having a better understanding. Well, but then again, I mean, I can only achieve a better understanding by keep trying. So, yeah, I'm just showing my like the confusion and process in plain sight. So I think this is valuable. So basically, this identity brings us to the main point. This combination, being a component of a tensor, is a tensor in its own right. This alone should signal to us that this combination ought to take the place of the partial derivative as the differential operator for measuring spatial variability. Besides being a tensor, the combination, yeah, is decidedly preferable. Yes, we already seen that. It is actually represents a component of the derivative of the vector field U. It is able to do so by referencing only those objects that are available in the coordinate space. I'm so close to finishing my laundry. Victory is near. Good for you. So this is possible thanks to the term containing the Christoffel symbol. This is possible thanks to the Christoffel symbol, which can be said to account for the variability of the accompanying basis. Yeah, that's the thumbnail. That's the thumbnail of the video, because I was trying to, figure out a nice description for the covariant derivatives. Right? I was like, okay, this is. I did some research. I did like an AI overview, okay, in Google, and it says this is a good way to describe covariant derivative in one sentence. It's derivatives accounting for changing a coordinate basis. All right, so here you have a contravariant vector, right? And this is just the naive differentiation, which of course is not a tensor. To make that a tensor, you add this correction term. This is the correction term. So the correction term for the contravariant tensor is positive, whereas the correction term for the covariant tensor is a negative. So that's the idea. Yeah. So yeah, that's the covariant derivative in a at the first understanding. I think this is good enough for us for now. Of course, this needs to be practiced with more exercises. Okay, we already seen that, right? And now we're doing, okay, so now we're doing it for the covariant component. As mentioned, you should pick up a minus sign. That's another law. I have to check out whether this is true in a general Riemannian space with a little g, okay? Because I remember, yeah, if we go back to the book, here, now I'll come back to this, okay? But if we go back to the book, I remember they, here, you see, they do it in a Euclidean space first and then Riemannian space. Yeah. So, I mean, it's still valuable. It's still, of course, still valuable. I just don't know whether this definition of the Christoffel symbol still works in a Riemannian space. I just don't know. But this is still, I mean, as far as Euclidean space is concerned, a very useful way to understand covariant derivative. So the underlying vector space is invariant, right? It's independent of coordinate system, and now you impose a coordinate system. Right? You want to see how the vector field changes relative to the coordinate. But the problem is, in general, the coordinate system has changing basis vectors. Right? Just like in the polar coordinate, right? We emphasize that many, many times. Right? Cartesian coordinate is special because everywhere its basis vector is the same. Right? So if we go to, say, where's our, yeah, the 730s. Do you have a picture there? No, we don't. 731, maybe. Do we draw a picture there? Perhaps not this one, huh? Yeah, this one. Yeah, we emphasize that. Yeah, in the polar coordinates, for example, if you change your position, the basis vector changes. Right. Here in the polar coordinate, the basis vectors are, let's say, your position vector. Here we can talk about position vector because Euclidean space is flat. In a general Riemannian space, you cannot talk about the position vector. It makes no sense. But here, let's just say the position vector is big R. Of course, this is an invariant, right? It's just the distance is just a position vector. Displacement. So R depends on R and theta. You can describe the position using coordinates. So now dr, the dr is what? Is partial derivative dr times little dr plus partial derivative dr over d theta times d theta. So that's the basis vector. And often if I recall correctly, in Riemannian geometry, you just write a basis as d over dr, d over d theta. That's called a basis. That's called a basis. Anyway, the basis changes from point to point. Right? So that's what makes things difficult. Okay. So here, going back to the book. Right. Here, yeah. Going. Yeah. I just don't know whether the change in the basis vector as a linear combination. Yeah, this one. Right here. The change of the basis vector as a linear combination of the basis vector themselves is still possible in the. I don't know whether this is still possible in a curved space. I don't know. But in Euclidean space, of course, this is possible. Because, like here, the change in the dr and de are still in the plane, right? You can write that as a linear combination of er and e theta. Of course, you can do that. But I don't know whether this is still possible in the general Riemannian space. I don't know whether this definition still holds true in a curved space. I have no idea what any of this means. I hope you'll understand it. And guess what? I'm not any better. Like, perhaps a little bit better, but what I do want is this is my, so to say, preparation. If you can follow it, then great. But this is meant for creating more structured videos. You can so think of these live sessions as behind the scene. Okay, as behind the scene, as the more polished videos are the dishes served on the dinner table. This is what's happening in the kitchen. Okay, in the kitchen, not everything looks tidy. Okay, and sometimes it's yeah, you know what it's like. Okay, so now we have the formal definition. So now we have the formal definition, and this is a notation with this nabla symbol. Right? We use the comma symbol. Right? Here you use the nabla. So perhaps this is a more modern definition. Okay, a more modern notation. Okay, so okay, so yeah, that's very cool. Perhaps we should do a little bit of an earlier part of the book to really understand what is going on. But I really like this. This is really slow, right? This is really slow, and it's very, how should I put this? Unlike the book by Lass, there's intuitive commentary going on, right? In the Lass's book, of course, the algebra works, but it feels like magical, right? It's not clear what the geometric meaning is, right? All we know from Lass's book is that, oh, you want to cancel the second derivative so to create a tensor. But what does it mean? It doesn't say. Right? Even though here, Pavel Greenfield's definition of the Christoffel symbol is a little bit different from ours, I think it's great for us to at least to get a hold of what this means. Right? So now this is extremely awesome. In particular, like this one earlier here, this derivation right here was extremely awesome. This one right here, it tells us what this combination is. The combination is an expansion coefficient. This is an expansion coefficient of the rate of change of an invariant vector field. So pretty awesome. So now we have a meaning of the covariant derivative. So basically, if you say swap U to a tensor field, not a vector field anymore, it's a tensor field, then it should measure the tensor field variability, the variability of a tensor field along the coordinate lines. Right. Because coordinate lines are also geometric objects. They're curves in space, so you're moving along a curve. Right. like here, draw the picture. We draw the picture here. So you're moving along the curve. You want to see how far the vectors change. So I remember earlier I asked ChatGPT a question. Let me just go find that earlier chat here. Perhaps that's also useful for you guys as well. Yeah, AI can be a friend. It's not just taking mathematicians' job. They can help with our understanding as well. I'm not an AI doomer, all right? So I remember having this conversation earlier. Is this one? Yeah. I said, can we express the covariant derivative as a limit? Right? Because for me, like, this should perhaps be the first thing that you should be able to answer. Right? We learned derivative as a limit. Can we express the covariant derivative as a limit? It says, yes, in fact, many geometers would say that the limit definition is a fundamental one. The difficulty is that vectors at nearby points live in different tangent spaces. So before taking a different quotient, we first must identify those tangent spaces. Right? This is very meaningful because if you look at the picture we've drawn here, at this point you have a little tangent space going on right here. This is a tangent space. So let's say if we want to calculate how much or the rate at which the vector changes when going from here to here, right? They live in different tangent spaces. Right, so that's the first difficulty here. And this is the ordinary derivative, of course. Right? So for the vector field, the subtraction is meaningless. So this is, by the way, gamma is a curve. So think of gamma of t as a curve like this. So you're moving along a curve in the curved space here. So imagine this is gamma, okay? And if we want to do the subtraction, how the vector, okay, the vector, the new position, that is v of t plus h, v of gamma, the vector at this point, the new location, v of gamma at t plus h, minus v of gamma t, right here. If you want to calculate the difference, it is meaningless because they live in different tangent spaces. They're in different vector spaces. How can you do the subtraction, right? Because we're not even assuming there is an ambient Euclidean space. They're not in the same vector space, so you can't define algebra here. So what can we do? We're going to introduce parallel transport. And this is, by the way, also important in information geometry. Okay, the idea of a parallel transport will be formalized. But let's just keep going. So perhaps intuitively, this should be very suggestive in the sense that you're transporting the original vector in a parallel manner along the curve to the other tangent space, so you can do algebra, so you can do subtraction. So that's the idea. Suppose this is once again a very vague description. So suppose we're transporting back, not forward. We're transporting the vector at the new tangent space to the old one. So going back to the picture here, you're transporting the vector, this one, back to this position. So that's the geometry. Suppose P of t plus h to t denotes the parallel transport along the curve from the new position back to the old position. So now both vectors lie in the same tangent space, so subtraction makes sense. Okay, so the covariant derivative is now the following. Big dv over dt, t is the parameter of the space, sorry, the t is a parameter in the curve. Okay, so now you're doing the transported version, right, of v of gamma t plus h. So now the transported version and v of gamma t lives in the same tangent space, so you can do subtraction. It's probably the cleanest geometric definition. Okay, why do Christoffel symbol appears? Why does it appear? So this is basis expansion, as I was saying. Right? D over dxi, this is just the basis vector. This is basis vector, and vi is the coefficient. Parallel transport over a small interval satisfies the following. Wow. I didn't know about that part. I didn't know about that part at all. So this is the new basis vector. You see, this is a d over dxi when t is t plus h. So that's a new basis vector. So that's, in this picture, this would be a basis vector of this tangent space. And now you're transporting it back to the old tangent space. And it's equal what? It equals the old tangent, the basis for the old tangent vector minus this term. This is the Christoffel term. So the Christoffel symbol has to do with parallel transport in an infinitesimal arc. I mean, we don't know where this comes from, but perhaps this can be proved. There should be, we should be able to, there should be a way to prove this. But basically, that's another way to understand the Christoffel symbol. So according to Pavel Greenfeld, Professor Greenfeld, the Christoffel symbol is what? Christoffel symbol tells us the rate of change of the basis vector as a linear combination of the old basis vector. Okay? So perhaps this is the same thing, huh? Perhaps this definition of the Christoffel symbol is the same as one we've seen here. As of now, I cannot tell, but I strongly suspect this is geometrically very similar. Okay, and now here you do a Taylor expansion, right? This is a Taylor expansion. Vi of t plus h is vi of t plus h times the derivative plus OH. And what can be substituted? Hold on, what can be substituted? Multiplying these together. What do you mean? Multiplying this. So this is the new basis vector. This is the new component. You multiplying them together, you get the new vector. Okay, that's cool. And how does multiplication work then? Yeah, Vi and this thing contract. Yeah, so use the new symbol k, new dummy index k, sure. What is this? Yeah, this is the second term. And now here we're doing the change of index. Yeah, we're just changing index, change this one to k. So multiplying this and this way, you create a dummy index I, change that to k, and now you can combine with this term, huh? But how do you get a minus? How do you get a plus sign? Isn't it a minus sign? Isn't that a minus sign here? What's going on? This is a minus sign. Hold on, this is component, so this is scalar. This is a vector. Why do you get a plus sign? Okay, if we take this as granted, Okay, if we take this as granted, then you do the subtraction, huh? The subtraction, you're subtracting v of gamma t, v of gamma t is just vk times the basis vector. And divided by h, you get this. But where do you get the plus sign? Yeah, so where are Christoffel symbols and coordinates representative? They're infinitesimal description of parallel transport. They describe how the chosen coordinate basis changes from point to point. Yeah, this is nice. This is all well and good, but where do the positive sign appear? So let me ask that. Question. The Christoffel symbol, guys, you know what I'm talking about? Here, this one times that gets this term. Yeah, no problem. But where do you get the positive? Like this one minus h, right? Times this one, you should get a minus sign. And this is h times h, so a higher order term, so we can put it in OH. See, h times gamma, and why on earth do we have this x dot here? Why do we have this x dot here? We didn't have that x dot. Might be hallucinating. I have no clue. Oh, x dot is natural. Actually, x dot is natural because this is over dt. Remember, here in our in what we're working on, we're differentiating with respect to here. Where the heck is my note? Yeah, we're differentiating with respect to coordinate. Here, you're differentiating with respect to time. That's why there's an x dot here. But the question, the Christoffel symbol, term in the parallel transport of the basis vector has a minus sign. Why after multiplication with the Taylor expansion of v dot I as a function of t plus h. Why after multiplication? Yeah, we get a plus sign in front of the Christoffel symbol term. What's going on? You know, this is the damn thing with AI. They always agree with whatever you say, even sometimes when you're wrong. So the plus sign, where do we get the plus sign? Okay. Okay, so this is fine. Yeah, we're okay with that. That's the basis vector. Yeah, this is the expansion. This is Taylor expansion of the component. The basis satisfies this. I don't have a formal definition of the parallel transport. I don't know what this means. So this means, is there a mistake here? This is a parallel transport of the basis vector, and it should be a plus sign. So this means that, yeah, going back here, this should be a plus sign. This is the parallel transport of the, hold on a second. This is transporting backward, right? So it's from t plus h to t. You have a minus sign. But this is a plus sign? Okay. Then if this is a plus sign, it means the earlier message has a mistake. Then the multiplication would just pick up a plus sign. Yeah, sometimes it happens, right? So to firmly confirm this, you need to actually show this. You have to actually show this using a definition for parallel transport and whatnot. But parallel transport is not covered in Harry Lass's book. It's not in there. So you need some other sources to describe this. Okay? But anyway, I think now we have a vague, sort of say intuitive understanding of the geometry. Right? We know how to do algebra. We know how to do algebra. So, and how to derive this algebraically, derive the covariant derivative algebraically. And we have some kind of geometric interpretation of the covariant derivative. I think that's pretty good. Let me just do one exercise, okay? I want to do one exercise. So in Professor Greenfield's book, I noticed an exercise which is quite interesting, and I wanted to share with you guys, and hopefully we can solve it. So here. So our goal is to show that the acceleration along a curve is a tensor. We want to show that acceleration along the curve is a tensor. So that's our goal. Exercise. This is from Greenfield's book. The original book, 2013. Exercise 121, as well as exercise 82. Okay. So let's first start with exercise 82. Okay. So here, it says consider a particle moving a parametrized curve along a curve which is zi. In Professor Greenfield's book, z is the coordinate. Okay, we use x, he uses big Z. Big Zi is a function of t. T is time. Okay, and we want to show that the vector v show the component vi of t of the vector v is simply vi of t equals zi dot. Just the time derivative of the coordinate. Okay? So there's that. Okay. Because this is still in the Euclidean space, in this part of the book, the textbook is still dealing with Euclidean space. So we can say something about the position vector. In general, there's no such thing as a position vector, but here in Euclidean space, we can say there's a position vector. So the position r of t is zi of t times the basis vector, which is z vector I. This is the basis, which may change from point to point. Okay, so Euclidean space, but nevertheless, the space is flat. Okay, space is flat, so you can talk about position vector. Say this is the origin. But the coordinate lines may not be straight. Okay? Say this is z1 equals constant. This is z2 equals constant. And the basis vectors are tangent vectors along the coordinate lines. So, as we were saying, z1, z1 is, should be, along this is z1 is constant. This should actually be z2. z2 vector is dr over dz2. So that means keeping z1 constant and change z2. That's exactly this one. And this green vector is basis vector z1 dr over dz1. Okay, Euclidean picture. Anyway, so that's the position vector, and then we differentiate. V is r dot. V is of course r dot, and now differentiate this. Should we what I'm worried about is that because the position vector changes over time, of course. If we differentiate this, we get z dot I of t. Use the product rule. Zi and then plus zi of t times zi dot. So what is zi dot? Well, zi dot, because zi changes from position to position. So it should be, so this should be dzi vector over coordinate dzj, and then zj dot. But this is the you can express this in terms of Christoffel symbol from the book here. Christoffel symbol, where's the definition? Yeah, right here. It's the definition of the Christoffel symbol. So this term should be gamma m with bottom line with bottom here ij. Okay. Let me just. It says this is a definition of the Christoffel symbol. I want to put it on the side. This is Professor Greenfield's definition. We define Christoffel symbol from the metric tensor using the geodesic equation, but here we use this definition of Christoffel symbol, which in my opinion is more geometric. Is more, let's say, intuitive. Okay, that's what I mean. Zi dot times Zi vector plus Zi. Okay, so you should have a Christoffel symbol, big gamma m, I at the bottom, j at the bottom, times z m, yeah, and zj dot. Is that right? Should be z. Actually, it should be zj uppercase. Upstairs, coordinate dot. Yeah, that's more like it. But this isn't what we're looking for, no? This is a vector here. Can we swap indices to combine the terms? I guess we can. Let's write the first one as z dot m, zm vector plus zi big gamma m ij, zm vector z dot j. So combine the coefficient, you got z dot m plus zi gamma m ij z dot j times zm. But this is not the component. Huh? This is weird. This is not what we wanted. It should be just z dot. Why on earth do we have this term here? Did I misunderstand something? Okay. Guys, I think I'll have to check with AI and see what's going on here. Okay. Let me start a new chat. So, because I'm a little bit confused here. Okay. So consider a trajectory of a particle. Zi. The component of the velocity. We wish to show that the component of velocity, components say vi of the velocity is zi dot. Okay, so I am not assuming Cartesian basis. I mean, the space is Euclidean. I'm not assuming this is a Cartesian basis. You see, if it's Cartesian basis, of course, then EIs are all constant. Then it's just, this is trivial. What I'm saying is, so is, if, let's say, if Zi is curvilinear, is a curvilinear coordinate, is the vector coordinate system, is the vector component still vi, still zi dot? Okay. Why? So that's why, right? That's what we are struggling right now. So apparently that's just the chain rule, huh? Why is that just the chain rule? Oh, actually, this isn't correct. This isn't correct because this would already imply a constant basis vector. This is actually incorrect. Okay, so I started from the wrong premise. This is incorrect. This is incorrect. So if I, yeah, here I already assumed zi's are constant vectors. That's not right. That's not right. So screw that. This isn't correct. So yeah, v should be r dot, which should be dr over dzi times zi dot. Yeah, but this is the vector component here, as this picture shows. So this is zi dot times zi basis vector. Yeah, no, that's much better. Okay, so this is done. This is done. Okay, so we now have the velocity, and now let's differentiate the velocity to get the acceleration. Okay, so that's the next exercise. The next exercise shows that the component of an acceleration, right, the component of the acceleration is given by the following. And then next, show the component ai of t of the acceleration big A vector is the following, is ai equals dvi over dt, right? Just the ordinary derivative of the velocity component plus gamma ijk vj vk. Okay, that's the acceleration. So solution for that would be differentiating v. Let's differentiate the v. So a, by definition, is v dot. Okay, v dot would be d over dt of the vector zi dot. Hang on, this is incorrect. You got two lower indices, so summation notation doesn't work. I should be upstairs. Yeah, now it's better. Use a product rule. Use a product rule, so this way you get. Hang on. Actually, you know what? Let's write this as v. This is vi. Vi is the component. Okay, let's change that to vi. Okay, vi, and this way you get vi dot zi vector, and then vi times the time derivative of zi. The time derivative of zi vector, in which case should be the chain rule dzi over d j upstairs, and then times zj dot. But zj dot is just zj dot is just v dot. Is just vj. Yeah, zj dot is just vj. So substitution. Okay, vi dot zi dot zi vector plus vi, and now use the Christoffel symbol, gamma m ij zm vector. Okay, nice, and this is vj as said. Okay, and now time to swap the indices. Okay, exchange m and I. You got vm say vm gamma I. Yeah, I want to change gamma and change. Hang on, I want to change m, exchange, switch I and m. Okay, that's what we're doing. M downstairs, j here, zi, vj. Okay, cool. And now we can factor zi vector. So it would be v dot I plus gamma I mj vm vj vm quantity times zi vector, and this is exactly the component here. This is exactly the component of ai as needed. So we're done with this part. Okay. So now we need to show this is a tensor. Next, show the AI is a tensor. we need to show the tensor. We need to verify the transformation law. That is to say, verify I bar. Yeah, bar. So I'm now mixing the notation in two textbooks. Okay, I'm using the bar as a new, because I hate adding primes and it's difficult to see. Just use prime. Just use bar. So a bar I want to show this is a alpha. The Jacobian would look like d new over d old. So d z bar over dz, and then install the subscript. I should be on top, alpha should be at the bottom. Okay, so that's what we try to verify here. Okay. Okay, so, well, just apply the definition of AI bar. AI bar, right? So we want to show this is a vector. Yeah, just want to make sure this is the correct question, okay? Yeah, the acceleration of a particle moving along the curve is a tensor. I want to show this is a tensor. So AI bar, by the definition, should be V bar dot I plus gamma bar I mj V bar j V bar m. There you go. Yeah. So want to use the transformation law for V. What's the transformation law for V? Because of V is V is a vector, contravariant vector. V is a contravariant vector, so Vi satisfies the transformation law. So V bar I should be V alpha dz bar I over dz alpha. We should have that, so let's plug that in. Okay, so you have d over dt of V bar I, just V alpha, times dz bar I over dz alpha. Okay, and then plus the Christoffel symbol, the new Christoffel symbol. So the Christoffel symbol should, the new Christoffel symbol. Well, that's tricky to write. Let's find it here and adapt to our notation using z instead of x. I'll finish this exercise and we'll call it a day. Okay, it's about time we finish the stream. So big gamma here should be, the new big gamma is big gamma. All right, and you have, say, I'll fix the index later. So you got d z bar over dx dz, okay, and then dz over dz bar, dz over dz bar. Okay, we'll fix the indices later, okay, and then d square z over dz bar times dz bar dz. That's just the Christoffel symbol. Let's fix the indices. Okay, so I on top, m and j at bottom. Okay, nice. Let's do alpha, beta, gamma. Okay, so the first term is done. The second term here we have, what's that? I m j, I here, m here, and j here. Sigma here, sigma here. Okay, so that's cool. The Christoffel symbol is now taken care of, and the two more Jacobians, two more transformations. So you got, this is Vj, right? Vj, so alpha is already used. All right, let's use a different letter. Yeah, alpha is already used, so let's use, say, V lambda, and this is Vj, so this is dz bar j over dz lambda. And lastly, v bar m, let's use a different letter, say sigma is already used, so let's use mu, okay? So v mu, say v mu dz bar m over dz mu, okay? Okay, so we want to simplify this. Okay, so we want to simplify that. Let's do the product rule in the first term. The first term by the product rule is v dot alpha dz bar I over dz alpha. Okay, now we're cool with that. And next up, v alpha unchanged, and then you differentiate this. So you need a second derivative. And for that we write d squared z bar I over dzj dz alpha, and then derivative of zj with respect to t, so that's just zj dot, but zj dot is vj. Right, this is vj. We'll keep in mind in that. So this is vj. Okay, so let me just put it on the side. This is vj. Okay, and now here we need to see if there's anything we can do about these Jacobians. So the first term, look at the Jacobian here. Do we have anything that we can cancel? Yes, it does seem like we can cancel some stuff, because here you have a dz gamma over dz bar j, and here you have a dz bar j over dz lambda. So this is useful. These two will collapse to a Kronecker delta. So that's very useful. Anything else? Yes, there's something else. Here, dz beta over dz bar m, and this term will also collapse to a Kronecker delta. Okay, so let's write that down. So this is gamma, alpha, beta, little gamma. Just want to make sure there's nothing else. Okay, so far so good. So you have dz bar I over dz alpha. dz alpha, dz beta over dz bar m, and the last term, then the last factor, gives you the Kronecker delta beta mu. Okay, and the force factor dz gamma over dz bar j, and this factor dz bar j over dz lambda will give you delta gamma and lambda. Okay, cool. What else? Well, just v lambda and v mu. And now you just swap indices for those two. Okay, so we'll do that in a second. But what about the last term? Anything happening in the last term? In the last term, we have, well, the second derivative, we can't do much about that. Just put it right away. Say d square z sigma over dz bar m dz bar j. Okay, what about the Jacobian? Can we do something about that? Do something about, say, this thing right here. Remember, I is supposed to be free index, so this one shouldn't be. No, it doesn't seem like we can do much, huh? Doesn't seem like we can do much. That's okay. That's okay. We're just gonna leave the Jacobians together. Say d z bar j. Actually, you know, it's dz bar I over dz sigma times dz bar j over dz lambda, and then times dz bar m over dz mu v lambda v mu. Okay, time to combine the terms and see what happens. Okay, here what we're saying is as follows. So you can consider the following. So here, first of all, we wanted to swap the indices. This just gives us v gamma and v delta. No? Yeah, v, not delta, but v beta. V beta, okay? And gamma and alpha are contracted. So I think the idea is that this term and this term should cancel. I think that should be the case, but let's verify. Okay, so the first and the third term together. Okay, these two terms together. So let's try to group things. Okay, this is v dot alpha, and here you have plus gamma. Okay, plus gamma alpha, beta gamma, v gamma, v beta together times dz bar I over dz alpha. Okay, and the second and the fourth term, I think they should cancel just like how we did the contravariant vector derivative, this one here. They should cancel very much in the same manner, but let's just check. Okay, so here, at least we have a common factor here. Do we at least have that? Yes. We have, for example, here, we see we have indices alpha and j being, you can swap the dummy index alpha and j. to be lambda and mu. So let's do v lambda v mu here. V lambda v mu, and then d square z bar I over dz lambda dz mu. Okay, that's cool. And now, yeah, and it's just this big term here. We claim this is 0. And once again, use the shenanigan of differentiating Kronecker delta. It should give us a 0. I have faith in that. Even though this looks horrible, but I think this should be 0. We claim this is 0. Isn't that the same thing we've shown earlier? If that's the case, we can just borrow it here. Right? Like here we differentiated the Kronecker delta. If we want to say get rid of this term, we should be able to do that as well. Right? So yeah, why don't we say multiply. Let's call this thing, give it a name. Can we give it a name? Say this thing, okay? Okay. This multiplied by a, I want to get rid of this. I want to get rid of this. So here, notice that beta is free. So I want to get rid of beta. Multiply by dx beta over alpha. I cannot use alpha. Alpha is free. So anything else I can use? Say lambda. Lambda is fine. Yeah, lambda is fine. So multiplying that, it gives us a Kronecker delta I lambda. So this I gets swapped to lambda. So d square x alpha over dx bar j dx bar lambda. So that's the first term, and the last term would be just nothing you can do about that. Just this multiply. Hold on. Nope. Yeah, multiply that by dx beta over dx lambda. And compare this with what we need in the acceleration. Perhaps there's a better way to do this, but this should work. This is 0, okay? So let's take a look at this identity and see what we have in the acceleration. I think they should be the same. Here. Check this out. Not quite, huh? Not quite. Not quite. But yeah, if we just treat z bar as x, z bar as x and z as x bar, Are they the same? Are these two the same thing? Let's take a look at the indices, okay? So here, how many indices are free? Lambda is free. Yeah, lambda is free. Mu is free. I is free. There should be three free indices. And over here, there should be three free indices as well. So let's check. What are the contracted ones? Sigma is contracted. And M is contracted. Anything else? Lambda mu should be free. J should be contracted. Yeah, J should be contracted. Okay. Do we have the same contraction going on here? So basically, the second derivative should all have contraction. I, yeah, gamma, gamma, beta, beta. Boom. It's right. Yeah, it's right. So this is indeed the same thing, and this is 0. So this term vanishes. And guess what? And this is just A alpha. dz bar I over dz alpha. And we're done. So indeed, acceleration is a vector. Acceleration is a vector. And in particular, this term right here, this v bar, the product of v, this is what gives rise to the centripetal acceleration or circular motion. This is, remember, in centripetal acceleration, you got this v squared over r. And that's exactly what happens. So let's verify that, okay? Let's verify this is indeed, imagine you have an application. So the centripetal acceleration, is that how you spell it? Centripetal or centripetal acceleration, yeah. Centripetal acceleration is a manifestation of the Christoffel symbol in the polar coordinate. Okay. So here, I derived the polar coordinate Christoffel symbol a while ago. This should be well known. Maybe the 30s. Oh no, tensor here. Not this one. 30. Yeah. Yeah, we derived the polar coordinate Christoffel symbol here. Yeah, polar coordinate Christoffel symbol. Let me just summarize, okay? So in the polar coordinate x1, or actually z1, z1, z2 are r theta. Okay, and so you have the Christoffel symbol gamma ijk as follows. So gamma 1, 2, 2 is minus r. And gamma 2, 1, 2 equals gamma 2, 1, 1 is 1 over r. And everything else is 0. So that's the Christoffel symbol in the polar coordinate. Okay, let's apply that. Go here. Let's apply this result. The Christoffel symbol. Okay, so from earlier. Okay. So assume uniform circular motion. So assume uniform circular motion, that means r is constant. Let's say big R equals constant. And theta is just omega t. Okay, there's omega t, uniform circular motion. We all know this from high school physics. R is constant, theta is omega t. And then what happened? So then apply the velocity. Apply velocity. Formula. V dot equals Vi dot. Okay, Vi dot is Zi dot. Vi, not Vi dot, just Vi. Actually, let me write down the basis vector as well. Draw the picture. Here, I'm just saying. Okay, let's try not to impose another Cartesian coordinate, because that's it shouldn't be, right? It shouldn't rely on a Cartesian coordinate. So let's minimize in our drawing. So this is a basis vector r, not the basis, but the position vector r. So at this point, say r theta, what would be the basis look like? Well, the basis would look like this. D big R over dr, this is z1. Vector z1, that is d big R over dr. Okay, and this is z2. dr over d theta. Okay, so apply the velocity formula, which we derived earlier. V dot equals Zi dot. And you get V1, that is R dot, little r, which is 0. And V2, V2 would be omega, theta dot, which is just omega, constant. Okay, so that's the velocity formula, and apply the acceleration formula. Acceleration formula says AI is what? Is V dot I. Is V dot I plus the Christoffel symbol here. Yeah, that's the formula. Gamma ijk vj vk, right? Okay, so let's apply this to A1 and A2 respectively. Remember what this means. These are components. For example, the velocity component says there is no radial component. And the angular component is a constant, which is exactly the case if you think about circular motion. There's no radial velocity, and the tangential velocity component is a constant. And the tangent, and in particular, velocity is what? Velocity together, let me just write that as a vector. These are components, remember. These are, velocity component, and as a result, from our earlier vectorial formula, V should be Vi times the basis vector, Zi. Okay, and this is a summation. The first term v1 z1 is 0, so you just get v2 z2, which is just omega times what? Omega times dr d theta. Omega times dr d theta. That's it. So it says it's the basis vector in this direction times omega. Okay. All right, cool. So, and now let's apply the acceleration formula. The component A1 should be what? Should be V1 dot. V1 dot, that's a free index. 1 is free index, and gamma 1 jk vj vk. Gamma 1. Okay. Well, as I said earlier, because when the upper index of big gamma is 1, there's only one non-zero term. So this is just v1 dot plus gamma 1, 2, 2. That's the only non-zero. And then times v2, v2. In principle, there should be 4 terms here, because you have 2 indices j and k, and they both run from 1 to 2. So in general, there should be 4 terms, but here there's only one non-zero term, so it's just gamma 1, 2, 2, v2, v2. And guess what? This is just minus r omega squared. Just the well-known centrifugal acceleration. So that's a manifestation of the Christoffel symbol. Okay. This is v2 times v2. Okay, let's calculate the other component. So a2 is v2 dot plus gamma 2 jk vj vk. Well, v2 dot is what? v2 is constant omega, so that's a 0 here. Just omega dot, which is 0, and plus, okay, what's the non-zero here? Well, you have 2 terms. That's gamma 2, 1, 2, v1, v2, plus what? Plus v gamma 2, gamma 2, or 2, 1, gamma 2, 2, 1, v, v2, v1. But v1 is 0, so both term vanishes, and omega is 0. Omega is constant, so that's a 0. So so it vanishes. So basically, for uniform circular motion, together, the acceleration, if you combine both components, a as a vector, ai zi vector, it should be what? It should be minus r omega squared times the position vector dr over dr coordinate, which is exactly in the opposite direction. It points towards the origin. So that's the centripetal acceleration. The only acceleration is the centripetal acceleration. So that's the application of this formula. Okay, so I guess we're good for today. Thank you very much for watching the stream. I can't believe there's still 16 people following the stream, like 6 hours later. Almost 5 hours, because I started at 6:30, didn't I? 5 hours later. Okay. Anyway, thank you guys very much for watching. We have first, I would say, passing understanding of the covariant derivative from 2 independent sources. Still, we have not yet reconciled them. Okay, but we're getting there. Thank you very much for watching. And next up, our goal is finally the curvature.